Welcome back to Sleep Nova. Sit back, relax, and enjoy the show. Silence. Darkness above, darkness below. An infinite and formless quiet. There is no up or down, no yesterday or tomorrow. Only a void, pregnant with potential, waiting beyond time. In the beginning, there is nothing. And then, in a single, trembling instant, nothing becomes everything. A blinding newborn light erupts from that void, birthing space and time together. The stage of reality appears out of the darkness, not empty, but carrying all that will ever be. The universe ignites with a flash, and the great cosmic drama begins. From that first furious moment, space itself unfurls, expanding, stretching, uncoiling faster than the speed of any light that will later travel through it. What was smaller than an atom swells to cosmic size in the blink of an eye. There is no outside to this expansion. Space is not expanding into anything. Space is simply growing, creating new space between everything, carrying galaxies in its flow like leaves on a rushing stream. In those first moments, the universe is a hot, dense plasma, a searing ocean of energy where matter and light are one, where the very laws of physics quiver in the newborn heat. It is a time before atoms, before stars, before any structure. Space is tiny, and space is absolute. All that exists is compressed in a blazing fog of creation, everywhere at once. The young cosmos swells rapidly. In a tiny fraction of a second, it doubles again and again, faster and faster. We call this fleeting epoch inflation, when the fabric of space-time ballooned mind-bogglingly fast, smoothing out any wrinkles. It's as if the universe took a deep breath and blew itself up like a balloon. Tiny random quantum fluctuations, minuscule imperfections, mere whispers of nothingness, were magnified to cosmic proportions. Those infinitesimal quantum jitters, born in absolute darkness, became the seeds of everything to come. From the very beginning, the illusion of nothingness hides creative power. Even empty space had flickers of energy, and those flickers grew to shape galaxies. Emptiness is never truly empty. It foreshadows all the structure that will later emerge. As space expands and ages, though it is only seconds old, it cools. The primordial fireball stretches out, its heat is diluted. Matter condenses out of energy, as if the cooling universe is crystallizing. In the first fleeting second, quarks join to form protons and neutrons. Within minutes, the first atomic nuclei appear. Simple hydrogen and helium, the lightest elements, fused in the inferno of the young cosmos. The universe is still a glowing plasma, a brilliant fog of particles and light intertwined. From the outside, though there is no outside, it would shine white hot like the core of a star. Time flows, seconds, minutes, tens of thousands of years. The cosmic fireball expands and dims from white hot to red hot to a warm glow. Space is now vast and cooling, filled with a hot nebula of charged particles. Light, which had been trapped, scattering in the dense plasma, now finds conditions gradually easing. 380,000 years after the beginning, a threshold is reached. The universe cools enough for electrons to settle into orbits around nuclei, forming the first atoms. And suddenly, the blinding fog of plasma clears. The universe becomes transparent. Light is free to travel onward, free to illuminate the darkness. The great cosmic fog lifts, and darkness, which had been drowned in light since the first moment, finally has room to exist again. In that moment, the first light of the universe bursts forth across space. A gentle glow permeates everything, the afterglow of the Big Bang. It is a fossil light, carrying the imprint of creation itself. Today, we still detect this primordial light as a faint whisper in the microwave spectrum, coming from all directions, the cosmic microwave background. It is a cold, faint echo of that once blazing fireball, stretched to longer wavelengths by billions of years of cosmic expansion. In its mottled, feeble glow are tiny temperature ripples, the fingerprints of those ancient quantum seeds that inflation scattered. In those ripples lie the blueprint for the cosmic web of galaxies yet to come. But after that first light shines forth, there is a long darkness. The cosmos expands into a dark age. No stars shine yet. The elemental hydrogen and helium gas, left over from the Big Bang, fills space like an invisible fog. Gravity is at work, slowly drawing the gas into denser patches, but to the mind's eye, the universe at this time is a black void, starless and still. Imagine drifting through a cosmos with no stars, no galaxies, only vast, cold clouds where atoms are beginning a slow dance under gravity's pull. In pockets of slightly higher density, the gas gathers, falling inward like dew condensing, growing hotter and denser at the center of those pockets. Eons pass in darkness, millions upon millions of years of cosmic night. Then, at last, there is light again. Gravity's patient work pays off. The first stars ignite. Deep in a collapsing cloud of gas, the pressure and heat soar until hydrogen atoms fuse into helium, and a newborn star's fire ignites. One by one at first, then in clusters, stars wink on, piercing the cosmic night. Imagine that moment. After ages of black silence, suddenly pinpricks of starlight appear like a scattering of gems on velvet. The universe's second dawn has arrived, the cosmic dawn. These first stars are giants, many dozens or hundreds of times more massive than our sun, burning their fuel furiously bright and hot. They live short, brilliant lives, pouring ultraviolet light into the once dark universe. Their glow begins to dissolve the primordial fog, breaking apart neutral hydrogen atoms around them. Space, which had gone dark and neutral, is once again filled with energetic radiation. The first stars live fast and die young. In a few million years, some of them exhaust their fuel and explode as titanic supernovae, enriching the surrounding gas with heavier elements forged in their cores. Their deaths trigger more starbirths nearby, and soon clusters of stars are gathering. Gravity, always the silent choreographer, draws stars into protogalaxies, small nascent galaxies merging and growing. Over hundreds of millions of years, these gather into the first galaxies, blazing with starlight and sometimes harboring newborn black holes in their centers. The universe is no longer a quiet, empty void. It is alive with light and drama. These early galaxies are chaotic and strange by our standards. Collisions and mergers are frequent, their shapes turbulent, but from their collisions, larger structures begin to emerge. The universe's once diffuse matter has now knit itself into stars, star clusters, and galaxies. The stage of space that was set at the Big Bang is now populated with a rich cast, brilliant blue-white massive stars, glowing red embers of dying giants, swirling nebulae of gas and dust, and nascent star clusters bound by gravity. Yet space itself remains the seemingly empty backdrop for all this action. We gaze between stars and see blackness. It is tempting to think of that black vacuum as nothing, mere emptiness between the things in the universe. But space is not a passive void. It is the fabric on which this whole cosmic tapestry is woven, and it has its own character and geometry. The shape of space can be bent. The flow of time can be altered. Space can carry ripples. We call them gravitational waves, when massive objects like black holes collide, and space can even tear or fold in extreme scenarios. In our everyday experience, space seems rigid and flat, Euclid's grid extending uncurved in all directions. But nature's true geometry is subtler. Decades ago, Brilliant minds on Earth realize that space and time are interwoven into a four-dimensional fabric called space-time, and mass and energy can curve this fabric. Gravity, as we know it, is not a mysterious force acting at a distance as Isaac Newton once thought. It is the shape of space-time itself, telling objects how to move. Matter, in turn, tells space-time how to curve. Picture space as a flexible rubber sheet. Place a heavy object like a star on that sheet, and it sags, creating a well. Now a smaller object, like a planet, moving nearby will roll toward the star, not because of an invisible force pulling it, but because of the slope in the rubber sheet. In reality, the planet is simply following the straightest possible path in curved space, a path called a geodesic, which appears to us as an orbit. As one physicist poetically put it, matter tells space how to curve, curved space tells matter how to move. If there were no space to bend, there would be no gravity as we know it. Space is an active participant in the cosmic dance, shaping the trajectories of planets, stars, and light itself. Indeed, light, which we usually think of traveling in straight lines, can be made to bend by gravity. When starlight passes near a massive galaxy or a cluster of galaxies, the space-time curvature there acts like a lens, bending the light's path. Distant galaxies behind get their images distorted and magnified into arcs and rings. We on Earth have seen this, subtle smears and halos in our telescope images that are gravitational lenses, proof that space around the foreground mass is curved. Even the sun bends starlight passing near its limb, an effect once observed during a solar eclipse, confirming Einstein's bold predictions. Space, when stressed by mass, warps and flexes. Under the weight of extremely dense concentrations of mass, space can even collaborate with time to perform astonishing feats. It can slow time's passage relative to elsewhere, so clocks run a bit slower deep in a gravitational well than far away. We have measured this too. A clock on a mountain ticks just slightly faster than one at sea level, where Earth's gravity is a touch stronger. The difference is tiny, but real. To someone falling into a very strong gravitational field, say approaching a neutron star or black hole, time on their own clock seems normal, but an outside observer would see their movements slow down dramatically. In the extreme, as our traveler nears the point of no return of a black hole, to an outside eye they freeze in time, hanging there at the edge of darkness. Space and time are intertwined strands, and what one experiences as time another can partly experience as a curvature of space. The two cannot be separated. They are simply different directions in the same unified space-time fabric. Look around you right now. You might feel motionless, but you are hurtling through space. Our Earth is falling freely in the sun's curved space-time, orbiting at about 30 kilometers per second. That's 108,000 kilometers along its yearly path. Meanwhile, the sun itself is racing around the center of our Milky Way galaxy at roughly 200 kilometers, steered by the curvature of space caused by the galaxy's mass. Even as you sit, you are carried on a moving platform through a continually evolving geometry of space and time. We are all space travelers, embedded in orbital dances we mostly take for granted. Gravity's choreography is ceaseless. Planets swing around stars, stars orbit galactic centers, galaxies themselves twirl within clusters. Space is not a static stage at all, but a dynamic player. And nowhere is this more dramatically evident than in the most extreme arenas of gravity, black holes. A black hole is a region where space curves so steeply inward and gravity becomes so intense that nothing, not even light, can escape once it passes a certain boundary, aptly named the event horizon. To form such a monster, matter must be crushed into a very small volume. Nature accomplishes this in the death of massive stars. When a star far heavier than our sun exhausts its nuclear fuel, its core collapses under its own weight. If there's no force able to halt that collapse, the core continues imploding to an almost infinitely dense point. a singularity, and a black hole is born around it. What does a black hole look like? For a long time, it was pure speculation. By definition, a black hole emits no light of its own. It is literally a black spot in space. Yet we now have glimpsed one indirectly, by photographing the glowing orbiting gas around it and seeing the dark shadow in the middle where the hole's gravity prevents any light from escaping. There it is, a circular silhouette against a swirl of hot, bent light. This image, humanity's first direct portrait of a black hole, reveals a cosmic abyss, space falling inward like a waterfall at the speed of light, carrying everything with it. Approach a black hole, and gravity's pull grows without bound. Far away, you might orbit it safely, as one would orbit any mass of that size. Closer in, however, space curves ever more sharply toward the center. Cross an invisible spherical boundary, the event horizon, and escape becomes impossible. It is as though you've been caught in a cosmic current that flows only inward. No rocket, no beam of light can fight its way out once inside that horizon, because space itself is rushing inward too fast. You could fire the most powerful engines in existence, but you would still be drawn further in, like a swimmer caught in a swift waterfall that even light cannot swim against. From outside, we would never see you actually enter. We'd watch your image redden and dim, your time slow to a crawl, asymptotically approaching that boundary, but never quite crossing it. Meanwhile, you, falling in, experience none of this oddness directly. You drift past the event horizon with no sudden jolt. It's just empty space locally, and plunge towards whatever lies at the center. What lies at the center? Our equations break down, much as they did at the moment of the Big Bang. We predict a singularity, a point of infinite density and zero volume, a tear in the fabric of space-time. It is a place where our understanding falters, where quantum effects and gravity meet in unknown ways. In a sense, the birth of the universe and the center of a black hole are kin. Both are singularities, edges of space and time that defy comprehension. If you fall into a black hole, you head toward this end of space and time, though end may not even be the right word. Before reaching that ultimate point, however, a physical object would undergo extremes. As you descend, the difference in gravity's pull between your nearer side and farther side grows enormous. For a feet-first fall, your feet feel a stronger tug than your head. This tidal force becomes so strong that it stretches you grotesquely, a fate whimsically known as spaghettification. Any object, an astronaut, a spacecraft, a planet, would be pulled into a long, thin strand as it approaches the singularity. First, your body would be pulled apart into pieces, then those pieces into molecules, atoms, and subatomic particles. It's a one-way journey of disassembly. Space funnels everything inward relentlessly, compressing all fallen mass energy into that central point. Outside the black hole, we observe its presence by its gravitational influence. Stars orbit an invisible mass. Gas swirls into a glowing accretion disk around it, emitting X-rays as it is heated to millions of degrees. Sometimes, paradoxically, black holes trigger jets, as some infalling matter gets redirected along magnetic poles and blasted outward as high-speed particles, announcing the black hole's feast to the universe. But nothing that crosses the horizon returns. The black hole grows quietly with each meal, its horizon expanding like a gaping maw. Black holes can be small, a few times the sun's mass, or monstrous, millions or billions of solar masses in galactic centers. Our own Milky Way harbors a calm, supermassive black hole at its core, around which stars whirl in tight loops, like planets on fast forward. In distant galaxies, some supermassive black holes actively devour matter and blaze as quasars, outshining their entire galaxy as infalling gas releases tremendous energy. Yet even these brilliant beacons are powered by what disappears forever from our universe into the hole's depth. If we consider the journey of a beam of light, from the moment of the Big Bang's afterglow to now, we see how space shapes destiny. Light released at recombination, the clearing of the primordial fog, has been traveling for nearly 13.8 billion years and only now reaches our telescopes as the cosmic microwave background. Some light emitted by a star, formed soon after that time, traveled nearly the entire age of the universe to arrive here. We have captured such ancient photons. The Hubble Space Telescope, gazing into what seemed like an empty patch of sky for days, revealed the Hubble Ultra Deep Field, an image speckled with nearly 10,000 galaxies, some so distant their light set out when the universe was a mere 5% of its current age. Every tiny smudge in that image is a galaxy, each galaxy containing billions of stars. The emptiness wasn't empty at all. It was full of galaxies too faint for earlier eyes to see. Space, even in a dark, supposedly blank patch, was teeming with the light of distant worlds. In this way, light is the great messenger, carrying stories across time and space. When we look out into the universe, we are also looking back in time. The finite speed of light, about 300,000 kilometers per second, means that even nearby objects are seen as they were a little earlier. The sun we see is an 8-minute-old sun. It takes light 8 minutes to reach us. The nearest star system, Alpha Centauri, we observe as it was over 4 years ago. The Andromeda Galaxy, faintly visible in the night sky, is 2.5 million light-years away. We see it as it was when early human ancestors were just learning to walk upright. As we peer deeper, the look-back time increases. Telescopes are time machines in this sense. Point a powerful telescope to capture a dim red smudge that turns out to be a galaxy whose light took 12 billion years to arrive. You're seeing a fossil image of that galaxy as it was when the cosmos was young. We have, with our modern eyes, seen galaxies only a few 100 million years after the Big Bang. Toddler galaxies flickering into existence. We have even heard the ripples of cataclysmic events far across space, merging black holes and neutron stars billions of light-years away, their collisions shaking space-time itself and sending gravitational waves that we detected here, tiny vibrations in our instruments. These too are messengers, different from light, telling us that space can ring like a drum when titans collide. Where does the observable universe end? As we scan further and further, we hit a horizon, not a physical edge, but a limit beyond which light hasn't had time to reach us in the 13.8 billion years since the Big Bang. We might imagine a sphere around us, about 46 billion light-years in radius today, which encompasses all we can, in principle, observe. Beyond that cosmic horizon, there may well be more universe, perhaps infinitely more. But it lies forever beyond our sight, because light, or any information, from those regions has not, and perhaps will never reach us. In a way, this horizon is like the event horizon of a black hole, but in reverse. It's a horizon, not because space is dragging things in, but because space and time began a finite interval ago for us, and distant regions are being carried away faster than light by the expansion. The most distant light we can see is the cosmic microwave background itself, a sort of luminous wall of fog marking 380,000 years after the Big Bang. We cannot see earlier than that with light, because earlier, the universe was opaque. Thus, the observable universe has a shoreline in time, a point beyond which our light boat cannot sail. As the universe ages, this horizon shifts outward. Light from slightly more distant regions will trickle in, but simultaneously, the expansion of space continues to carry distant galaxies away. We live in an expanding universe, a discovery made not even a century ago. In the 1920s, astronomers peered at fuzzy spiral nebulae and discovered they were galaxies outside our own. Soon after, Edwin Hubble found that these galaxies are, almost all, receding from us, with their light stretched to redder wavelengths. The more distant the galaxy, the faster it appears to flee. The straightforward interpretation: space itself is stretching, and with it, the distances between galaxies increase over time. Galaxies are not moving through space away from us, so much as space between us is swelling, carrying them apart. To visualize, imagine raisins in a rising loaf of bread. As the dough expands, each raisin sees its neighbors receding. There is no central raisin. Every raisin sees the same effect. Similarly, from any galaxy's perspective, space expands and other galaxies, beyond its local gravitational group, move away. This expansion was initially thought to be slowing down due to gravity, like an explosion gradually decelerating. Indeed, for much of cosmic history, the mutual gravity of matter did slow the expansion, but to great surprise, around 1998, we found that in the last few billion years, the expansion has begun to speed up again. The universe is not just expanding, it is accelerating in its expansion, like a car that, after coasting uphill and slowing, suddenly hits the gas and surges forward. The cause of this cosmic acceleration? We give it a name: dark energy. But truthfully, the name is a placeholder for an unknown phenomenon. Dark energy seems to be an intrinsic property of space itself, a sort of energy of the vacuum that, rather than diluting as space expands, remains constant or even grows, thereby driving space to expand faster. It acts like a repulsive gravity on large scales. About 5 billion years ago, dark energy's effect became dominant over the attractive gravity of matter, and the expansion reversed its slowdown and began accelerating. Today, dark energy constitutes roughly 68% of the total energy content of the universe, with invisible dark matter about 27% and normal matter only about 5%. Space, it turns out, is filled with this mysterious pressure that shapes the fate of the cosmos. What does an accelerating universe mean for the future? It paints a picture of an ever more lonely cosmos. Distant galaxies will recede faster and faster. In 100 billion years, observers in our Milky Way, or its merged descendant, might see no other galaxies at all. They will have slipped beyond the horizon, their light stretched into oblivion by the expansion. The sky would be largely empty, except for the stars of our own galaxy. Over trillions of years, star formation will cease as the raw gas is used up or locked in remnants. Existing stars will age and die, leaving behind white dwarfs, neutron stars, and black holes. Those black holes, over unimaginable timescales, will slowly evaporate via Hawking radiation, turning their mass into faint photons and particles until they too wink out. The universe will enter a deep freeze, cold, dark, and dilute. Matter as we know it will be dispersed. Only thin gas and wandering subatomic particles will remain, nearly motionless in the expanding void. This is the projected heat death, or big freeze, where the temperature everywhere approaches absolute zero and time stretches on without much change. It is a somber, profoundly quiet end, not with a bang, but with a long, drawn-out whisper. Of course, this assumes dark energy remains constant. If instead it were to grow stronger over time, an option allowed by some theories, the acceleration could become so violent that galaxies, stars, planets, and eventually atoms themselves are torn apart in a hypothetical Big Rip. Alternatively, if dark energy decays or reverses sign, the expansion could slow and stop, perhaps even reversing into a big crunch where the universe recollapses, maybe to bounce and begin anew. But present data hint at the endless expansion scenario. The eternity of space looms, seemingly, as an ever colder, ever emptier expanse. Yet all of these distant futures and far pasts are extrapolated from what we know now, and what we know now is constantly expanding as well. We stand on a small planet roughly 4.5 billion years into the life of a rather ordinary star. In a typical galaxy, among billions, and only a tiny sliver of the cosmic timeline includes our presence. As we reflect on the cosmic past and future, we realize how brief and precious the living present is, the era in which stars shine, galaxies thrive, and life can flourish. So far, we have looked outward at the immensity of space. But to truly understand space, one must also look inward, to the tiny scales where quantum reality dominates. If we zoom in far enough, does space continue smoothly forever, or is it grainy, composed of fundamental units? Our best understanding of physics suggests that on the scale of the Planck length, about 1.6 by 10 tons 35 meters, mind-bogglingly small, our familiar notions of distance and even direction might lose meaning. Space and time may become quantized, divided into tiny indivisible units like pixels of reality. At such scales, space-time may roil in a quantum foam, constantly creating and destroying microscopic black holes and wormholes in a frenzy of uncertainty. No one has seen this foam directly. It's far beyond any current experiment's reach, but hints emerge indirectly. The vacuum of space, we know, is not completely empty. Quantum fluctuations continually spawn virtual particle-antiparticle pairs, which flit into existence and then annihilate, all within the uncertainty limits of quantum mechanics. These ephemeral entities have measurable effects. They cause slight shifts in atomic energy levels. They contribute to forces like the Casimir effect, and in the early universe, they seeded the galaxies. In a sense, space at small scales is like a seething cauldron, not a tranquil void. Even nothingness is busy. Our mathematics suggests that space and time may become completely blurred at the Planck scale. If one could shrink down to that scale, geometry itself might lose the smooth character we take for granted. Directions and dimensions might tangle, cause and effect might become fuzzy. Is there an atoms of space-time, tiny discrete building blocks? We don't yet know the answer. We seek a theory of quantum gravity to unite general relativity, which rules the large-scale structure of space-time, and quantum mechanics, which rules the microscopic world. Various ideas, superstrings vibrating in extraspatial dimensions, loops of quantum space-time, brains, and bulk, have been proposed. They paint exotic pictures. Perhaps our 3D space is embedded in a higher dimensional reality. Perhaps what we see as particles are actually vibrations of tiny strings in a multidimensional space. It's speculative, but tantalizing. One implication of some quantum gravity ideas is the possible existence of wormholes, shortcuts through space-time. Wormholes are often imagined as tunnels connecting two distant regions of space, and potentially time, through a higher dimensional fold. If space can curve and bend, maybe it can bend so much that 2 points touch, creating a throat that links them. In principle, general relativity's equations allow such solutions. The Einstein-Rosen bridge is one example, essentially a black hole mathematically connected to a white hole elsewhere. But wormholes, if they exist at all, come with huge caveats. They appear to require negative energy, exotic matter that has less than nothing in a sense, to stabilize and keep them open. Otherwise, they pinch off instantly. So far, we have no evidence nature produces traversable wormholes. Still, they capture our imagination. A traveler stepping through a shimmering portal and emerging light years away, or in another universe entirely, is a staple of science fiction, a modern echo of ancient folktales of magical doorways. Whether traversable wormholes exist in reality or not, they serve to remind us how flexible space and time might be under extreme conditions. The universe is under no obligation to maintain common sense at all scales or all realms. Under the extreme strain of a black hole's singularity or the entire universe's birth, space-time could do things we never see in ordinary life. Tie itself in knots, connect distant locales, or spawn new regions out of seemingly nothing. For now, these possibilities remain theoretical. But consider how far our understanding of space has come. To the ancients, space was the domain of gods and myths, the vault of heaven, the realm of ether, an unreachable firmament. Philosophers debated whether a void could exist. Nature abhors a vacuum, it was said. For millennia, space was just the gap between Earth and the celestial spheres, not something with its own identity. Then came the scientific revolution. Copernicus, Galileo, Newton. The Earth moved through space. Space became an infinite stage in which stars were other suns. Newton pictured space as absolute, an infinite, unchanging grid, and time as absolute too, ticking everywhere uniformly. Over 2 centuries later, Einstein shattered that comfort. There is no separate space and time, only space-time, and it is not absolute, but relative to the observer, pliable and curved. Space could stretch, contract, twist, as it does around a spinning object, dragging inertial frames. Suddenly, the stage could participate in the play. The interdependence of space and time is profound. Travel fast through space, and you experience less passage through time. Moving clocks run slow. This has been confirmed with particle accelerators and precise atomic clocks on fast jets. Spend 6 months on the International Space Station traveling at 28,000 km/s, and you'll come back a few milliseconds younger than identical twin on Earth, the so-called twin paradox in relativity, resolved by understanding the different reference frames. Space and time exchange in equations depending on motion. They are 2 faces of one reality. One cannot bend space without affecting time and vice versa. We have built our GPS satellites to account for both special relativistic time dilation, because they move fast, and general relativistic time dilation, because they are higher in Earth's gravitational field. Without those corrections, your phone's location services would drift off by kilometers. Thus, even in daily technology, the unity of space-time is at work. Our minds, evolved for the mid-world of moderate scales, struggle to truly picture warped space-time or quantum foam. But we can feel a sense of it through metaphors. Perhaps imagine a vast, flexible fabric with ripples and folds. That's space-time. On it, tiny flickers everywhere. Those are quantum fluctuations. Now and then, a massive weight falls on the fabric, making a deep well. That's a star's gravity, deeper for a black hole. If the weight is heavy enough, it punches through, a black hole connecting who knows where. Meanwhile, the entire fabric is stretching, slowly in some places, faster in others, carrying along everything sewn into it. If you pluck the fabric, a big merger, waves spread out, gravitational waves. It's an imperfect analogy, but gives a flavor. The reality surpasses imagination. Space contains all of us, yet transcends our intuitive grasp. We ask, is space infinite? It might be. Beyond our horizon, it could go on forever, or it might eventually wrap around like the surface of a sphere in higher dimension. Current observations hint that space is extremely close to flat and likely infinite, but we cannot be sure. We ask, is our universe the only one? Perhaps not. Some theories of cosmic inflation suggest bubble universes, each with their own space and time, disconnected from ours. If true, then what we call space might be just one bubble in a frothy multiverse sea, a local space-time encapsulated by something larger. Yet these other bubbles would be forever beyond our reach. So this remains speculation. Let's return to the tangible, to ourselves in space. Humanity has always been intimately connected to the sky. For tens of thousands of years, our ancestors looked up with wonder and told stories about the stars. The Milky Way band was a river of souls, or a spine of night, or spilled milk of a goddess. The darkness was feared, but also revered. In a way, we were aware of space emotionally and mythologically long before scientifically. We felt small under the dome of stars. We felt the infinite above press down on the finite below. Now, in the modern age, we have ventured into space physically. We have sent our machines to other planets and even beyond the solar system. We have, for brief moments, placed human footprints on the moon, another world, and brought back photographs that forever changed our perspective. One of the most iconic, Earthrise, captured by Apollo 8 astronauts as they orbited the moon. In that image, a barren lunar horizon arcs across the frame. Above it hangs the delicate blue marble of Earth, half lit against the black void. Seeing our world from afar, a fragile oasis in the vast darkness, was a profound moment in human consciousness. It was as if life's gaze had finally turned back upon itself and saw its home in context. A tiny, beautiful, lonely planet, suspended in endless night. Astronauts often report a powerful overview effect, a cognitive shift, when viewing Earth from space. They describe a deep sense of the unity of our species and the fragility of the biosphere. National boundaries vanish, petty conflicts seem absurd. There is just one world, shimmering blue with oceans and white with clouds, sitting in the velvet black of space. The thinnest wisp of atmosphere is all that separates life from lethal vacuum. Beautiful and fragile are words that come up again and again. Looking outward to the stars and seeing a vast emptiness, then looking back to Earth and seeing all of life in one tiny globe, must stir an existential awe unlike any other. It is humbling and illuminating. In space, our bodies and minds face new challenges. Those who have traveled to orbit find that their sense of up and down vanishes. In microgravity, astronauts must relearn how to move. At first, many feel a disorienting nausea as the inner ear's cues conflict with what the eyes see. Space adaptation syndrome, essentially motion sickness in freefall. The fluids in the body shift upward without gravity pulling them down. Faces become puffy, legs thin out, bird legs. Over time, bones and muscles, no longer bearing weight, begin to weaken. Astronauts lose bone mass at a rate of about 1% per month, despite exercise. Their muscles atrophy as well. Their hearts slightly shrink because pumping blood doesn't take as much effort. They must work out vigorously every day to mitigate these losses, using resistive devices and cycle ergometers. Otherwise, returning to Earth's gravity would be difficult. They might faint or struggle to walk after long missions. Despite all precautions, long stays in space do alter the body. Some experience degraded vision due to fluid pressure on the eyes. Cuts and wounds heal differently. Sleep can be disrupted by the lack of normal day-night cues. There is also radiation. Beyond Earth's protective magnetic field, cosmic rays and solar particles zip through spacecraft and human flesh. Over months, this exposure raises cancer risks and can cause subtle cellular damage. On a journey to Mars, astronauts would accumulate significant radiation dose, like getting many CT scans spread out over time. Shielding and careful timing to avoid solar storms are critical, but a degree of risk remains. Then there's the psychological dimension. Living in the confined, unchanging environment of a spaceship or space station for months, far from Earth, can strain the mind. Isolation, monotony, and the knowledge that home is hundreds of kilometers below or millions of kilometers away for future Mars explorers is a heavy burden. Astronaut crews are carefully selected for emotional stability and teamwork. They follow structured schedules to keep busy and maintain a sense of normalcy. But even the best can feel longing when they look out a window and see their home planet as a distant ball. One can only imagine the mixture of feelings, awe at the view, certainly, but perhaps also an acute loneliness or vulnerability. Earth, with all its familiar comforts and all of humanity, is out of reach except by radio. On the flip side, many astronauts report that while physically challenging, living in microgravity is also exhilarating. They speak of the pure joy of floating, of pushing off one wall and gliding effortlessly to the other side of a module. They develop a new spatial intuition. Down can be wherever you decide it is. They hang their sleeping bags on a wall or ceiling and drift off to sleep weightless. Some say it's the best sleep, like being cradled softly with no pressure points. Everyday tasks become novel. You must sip liquids from sealed bags. Since pouring a drink is impossible, it would break into floating blobs. And you must carefully corral every tool or spoon you use. If you let go, it might drift away and hide in some nook. There's a bit of humor and wonder in such scenes. An astronaut chasing a free-floating globule of coffee, slurping it like a lazy flying insect, or a stray pencil found bobbing behind a ventilator days after it escaped. Living in space is part high-tech endeavor, part childlike play in a gravity-free playground. All the while, just beyond the thin walls of the station or spacecraft is the void, a vacuum colder than 150 degrees Celsius in shade, blazing hot in sun, permeated by silence. Step outside on a spacewalk, and you are one tiny figure clinging to a metal island with infinite night in every direction. If you turn your visor toward Earth, you see grandeur, continents and clouds rolling by in silence 400 kilometers below, an immense sphere that fills half the sky. Turn away from Earth, and you face utter black, sprinkled with stars that don't twinkle, no atmosphere to disturb their light. They shine steady and innumerable, even against the blackness lit by the Milky Way's faint band. Some astronauts have described feeling a detached reverence on spacewalks, too absorbed in tasks to be emotional, until a pause allows them to drink in the view, and then, overwhelmed by the beauty and the sobering realization of being so far from home, protected only by a suit. It's a perspective few have experienced directly, but through their words and photographs, they've tried to share it with all of us. This leads us to consider consciousness and space in a broader sense. We, as thinking beings, always perceive ourselves as being somewhere. Our brains create a sense of space around us from sensory inputs. Even without sight, you feel oriented in a room by sound and touch. Our internal maps evolved in Earth's gravity, using down as a reference. In microgravity, astronauts must recalibrate their senses. Initially, many report feeling upside down half the time, or losing track of orientation. Yet the brain adapts. After a while, astronauts become ambidirectional, able to work regardless of rotation. The mind learns that in the absence of gravity, space is relative. Any way can be up. This adaptability of the brain shows how consciousness is tied to space, but not rigidly. We can adjust to new geometries. There's also a philosophical aspect. When humans left Earth, even just to orbit, it was the first time a living organism on our planet consciously detached itself from our ancestral home environment. That does something to the psyche. It enlarges the mental sphere in which we reside. Space travel expanded our consciousness outward, at least symbolically, to encompass more than Earth. We carry the aspirations and fears of our species into the void. As we floated above our world and looked back, we discovered not only knowledge, but a deeper understanding. An understanding that the pale blue dot below is singular and precious, and that the emptiness beyond is both hostile and beckoning. Some find in the enormity of space a profound loneliness. The universe appears indifferent, maybe devoid of other life, so far as we've found. The stars do not hear our cries. If we are indeed alone, the weight of cosmic solitude can be heavy. Others find in that same enormity a thrilling freedom, an endless frontier of possibilities and exploration. And many find meaning in the connection, that we are made of atoms forged in long-dead stars, that the iron in our blood and the calcium in our bones were birthed in stellar furnaces and supernovae. The universe is within us, quite literally, as much as we are within the universe. We are a way for the cosmos to know itself. Our consciousness gives the silent space a voice and awareness, if only in this tiny corner. From a certain perspective, space and consciousness are two sides of the same coin. Space is the external vastness we inhabit. Consciousness is the internal vastness that can contemplate it. Without minds to observe, would space have any meaning? Perhaps it would exist physically, but it would not be experienced. Through us, and perhaps other beings elsewhere, the universe gains the ability to reflect on its own existence. That thought can be humbling and elevating. We are small, yes, but not insignificant, because we carry the light of awareness. Throughout history, as we internalize the realities of space, our philosophies and religions had to adjust. Earth was no longer the universe's center. Humanity's place required a new narrative. We grew to understand that space is not up there. It's everywhere. The air between you and your screen right now is part of space. The gap between electrons and nucleus in an atom is space, and proportionally, a huge one. We ourselves are mostly empty space by volume. If an atom were blown up to the size of a stadium, its nucleus would be a grain in the center, and electrons like dust motes whirling near the stands. Everything else is empty. In that sense, we are made mostly of space. Solid matter is an illusion of scale. On the atomic level, there's vast nothingness with tiny, energetic particles dancing. The solidity you feel when you press your hand on a table is the electromagnetic fields of your atoms, repelling those of the table's atoms, never truly touching. You have never actually touched anything in the sense of your atoms contacting another's. There is always a tiny separation, filled with fields, with space. Thus, the space within is as important as the space without. We carry echoes of cosmic void in each of our atoms' architecture. We have talked about giant things and tiny things, about birth and death of worlds, about knowledge hard-won and mysteries remaining. Let us now zoom out again to a cosmic perspective and take stock. Here we are, small, curious, yearning, on a planet that orbits a star in a galaxy among billions, in a universe about 13.8 billion years old, and possibly infinite in extent. We have discovered that space is not empty, but filled with structure. Galaxies strewn like glitter, clusters and chains forming a cosmic web with great voids in between. Light crisscrossing the darkness, carrying memories of the past. Gravity sculpting the ballet of worlds. Dark matter lurking unseen, holding galaxies together. Dark energy pushing the fabric of space wider and wider. We have found that on the largest scales, space is remarkably uniform and flat. Yet on smaller scales, it is richly textured. We have found that space can bend around mass and even ripple when massive bodies move. We have found evidence that the universe had a beginning in time and has been evolving ever since, giving lie to the old idea of a static eternal cosmos. And we see that we are approaching some profound questions. Why does space have 3 large dimensions, and maybe hidden ones? What is the ultimate fate of space? Are there other universes, other spaces beyond ours? These questions border on metaphysics, but they also drive physics forward. Space is vast beyond imagination, yet intimately familiar. We move through space every moment of our lives. It is both an arena and an actor. It shelters us and can kill us. It separates us from other stars, but also connects us to them, since we share the same space. Perhaps the true nature of space is that it is relation. It is what exists between things and gives them their positions and sizes. Without space, no separations. Without time, no change. Together, space-time is the grand framework of existence. In the end, thinking about space always circles back to thinking about ourselves. We fill our maps with stars and galaxies, but inevitably mark an X labeled, "You are here." Contemplating the sprawling universe can make one feel small, yes. A single beat of a heart against 14 billion years, a single human against 100 billion galaxies. But consider, all those galaxies and all those years, and we can hold them in mind. Our minds, a product of the universe, can encompass the universe. That is a wondrous feedback loop. As we gaze out on a clear night, standing perhaps on a hill far from city lights, we see a sky that our ancestors recognized and yet did not. The Milky Way arches overhead, a river of countless stars. A smoky patch is Andromeda, our sister galaxy. Points of light are not gods or holes in a firmament, but distant suns, many with their own planets. We now know that the blackness between stars is not pure void, but filled with tenuous gas and dust, and further out, suffused with the faint afterglow of the Big Bang. We know that above us satellites are flying, and astronauts on the space station occasionally drifting across the sky as a fast-moving star-like dot. We might recognize planets wandering among constellations, Mars glowing red, Jupiter bright and kingly. With binoculars, we could see the Orion Nebula, a stellar nursery, or the glow of the Andromeda Galaxy. With a telescope, even more structure leaps out, spiral arms, clusters, comets' tails. We carry the collective knowledge that every one of those is a place in space, reachable at least in theory, governed by the same physics that governs our own world. The unity of physical law across space is another profound realization. A helium atom, on the edge of the observable universe, has the same spectral lines as one in our lab. Gravity operates the same in a galaxy a billion light-years away as here, though the relationships might be exotic there. This allows us to understand far-flung phenomena by studying local physics, a fortunate feature of reality. What of the philosophical meaning of space? To some, the vastness means freedom, an endless frontier that promises growth, expansion, adventure. To others, it means insignificance, a stage so enormous that we, the tiny players, seem to hardly matter. Space can evoke loneliness, as one imagines drifting eternally without finding another living soul. Or it can evoke unity, as when one sees Earth from space and realizes every human that ever lived did so together, on that one small globe. Space may feel eternal, making our lives seem fleeting, but it also casts life's brevity in sharp relief, perhaps encouraging us to cherish each moment more. Imagine for a moment a scene, perhaps in some future, or perhaps only in a dream. A person stands on the surface of Mars at dusk. Above, two small moons appear, Phobos and Deimos, racing across the sky. The sun, smaller and dimmer than on Earth, sinks below the rusty horizon, painting the thin sky salmon pink. As night falls, the stars come out in unbelievable clarity, no thick atmosphere to blur them. Our Milky Way glitters, and there, perhaps on the eastern horizon, a bright star slowly rises, with a faint bluish hue. It is Earth. Our explorer on Mars pauses in their work and gazes at that star. On that distant point of light is everything they cherish, all of humanity, oceans and forests, music and laughter, friends and family. An intense longing might well up, an emotional gravity pulling their heart across the void, but also a swell of pride or satisfaction. We came this far. Space allowed us to leave home, to see ourselves from new perspectives, to extend life's reach. In that moment, perhaps our Martian pioneer feels both utterly alone and deeply connected. The silence of the Martian night is profound, yet through the radio they hear colleagues, and in their mind, they hold the image of 8 billion souls back home, looking up perhaps at the same time, wondering about them. Every moment of human life has unfolded within space. We wake under a sky, we build walls and roofs to partition space for our comfort. We travel to work across town or across oceans, all movements in space. When a baby takes their first steps, when a loved one hugs you, when a dancer leaps, it's all spatial. Even when we dream, we conjure spaces in our mind's eye to move through. We cannot escape space. We are embedded in it as deeply as fish in the sea. And so space is not out there. It is here. The air around you, the room you sit in, the gap between the Earth and Moon, all of that is space. We already live in space. Earth is not separate from the cosmos, it is a part of it. Our planet is traveling through space on its yearly path, and we along with it. In a very real sense, space is home. It's just that, as the saying goes, we have to bring our own atmosphere. But once you realize Earth is an island in a vast ocean of space, and that ocean permeates every corner of existence, the notion of home expands. Home is the solar system that birthed our Earth, the sun that gives us energy, the protective magnetic bubble that shields us. Home is also the Milky Way galaxy that gave birth to the sun, and the universe that gave birth to the Milky Way. We emerged from the universe and remain a part of it, not apart from it. Thus, space is not foreign or hostile in the ultimate sense. It is simply nature on a grander scale. It can be dangerous, yes, but so can the depths of Earth's oceans or the peak of Everest. Yet we still explore and sometimes settle those places. Over time, we may extend our dwelling to multiple planets or space habitats, learning to create little Earth-like bubbles wherever we go. We will always need some of Earth's familiar comforts, gravity, water, air, ecological support, to truly thrive. But perhaps our ingenuity will let us transport a bit of Earth with us as we voyage farther. Standing at the twilight of one world and the dawn of another, we feel the eternity of space stretch out before us, full of mysteries, dangers, wonders. The stars above do not hand us their secrets. We earn them through effort and curiosity. And the reward is the cosmic perspective, a realization that the molecules in our bodies were forged in stellar cores and supernovae, that the heat keeping us warm originates in the nuclear furnace of an 8 light-minute distant star, that the very space enabling us to exist connects us to everything else. In this journey, from the silent darkness before the first dawn, through the fire of creation, the weaving of the cosmic web, the formation of stars and planets, the bending of space by gravity, the extremes of black holes, the expansion driven by dark energy, the quantum foam beneath reality's smooth surface, the dreams of shortcuts through wormholes, the courage of living in the void, to the vantage of consciousness reflecting on it all. In this journey, we come to a profound insight. Space is not empty. It is alive with story. It is the ever-present stage and actor where reality unfolds and evolves. It is the canvas on which time paints existence. As we conclude our exploration, imagine once more the deep silence of the cosmic night. But this time, it is not frightening or cold. It is serene, sublime, like the quiet of a vast cathedral, where the light of billions of stars are the candles. In that silence, you might sense something almost like a voice, not speaking in words, but in the language of awe and connection. It whispers that we are a part of this grand scheme, that the atoms in our bodies and the thoughts in our heads are woven from the fabric of the universe. We belong here as much as any galaxy or star. Looking up, you feel the weight of your body held by Earth's gravity, anchoring you to your home, yet your mind soars, unbound, into the stars. You are bridging the very gap of space with your awareness. In that moment, perhaps you understand that home was never just the ground underfoot or the walls around you. Home is existence itself, the totality of space and time of which we are an inextricable part. Space is not distant. Space is here. The universe is our address. And so, under the eternal light of billions of suns, on the edge of forever, we step forward. We carry with us the dreams of our ancestors who once looked up in wonder, and the tools and knowledge gained by daring to ask questions. The void welcomes and challenges us in the same breath. We may sometimes feel tiny, but we have something the endless reaches of nebulae and clusters do not. We have eyes to see them, minds to know them, and hearts to be moved by them. In that way, we give the universe meaning, and it gives us meaning in return. Space is the everlasting backdrop and the intimate medium of our lives. It is dark, but filled with light, empty, but full of treasures, silent, yet it inspires symphonies within us. As we end our story, we find ourselves back in the quiet darkness of a starry night, not fearful, but filled with reverence. Above, the Milky Way's pale band is a reminder of our galactic home. One of those stars is the Sun. Around it orbits Earth, and on Earth, at this very moment, a person stands in the dark, looking up, feeling the gentle night breeze, and understands, finally, that they are not outside of the universe looking in, but an inside part of it looking out. In the grand, dynamic living stage of space, we have always been home. Between the stars, there is a darkness deeper than night. We call it space. It seems empty, a gaping void stretching in all directions, a vast nothing. Yet that nothing holds everything. It cradles the stars and planets, the light and the dust, the silence and the echoes of creation. Space is the gulf between things, the separation that defines each object and moment, but it is also the connective tissue of the cosmos, an invisible thread weaving all things together. Without it, no distance could lie between 2 points, nothing to measure, no here, no there. With it, the universe can spread out and become. Space is absence and presence at once, the emptiness that gives form to what is not empty, the vast inky canvas on which galaxies are painted. Look up on a clear night, far from city lights. You see countless stars sprinkled on a black dome. The darkness between them feels like a void, but consider that this darkness is not mere nothing. It is a stage, an arena, a medium. It carries the faint glow of distant galaxies, the whispers of ancient light. It holds the earth in its invisible embrace and extends beyond the farthest horizon our eyes will ever behold. In that darkness, every possibility exists. As an old proverb teaches, a cup is useful only because of the empty space inside. So too, the emptiness of space is what allows stars to shine, planets to orbit, and life to breathe. Space is the womb of the world and the ocean in which we float. We have always been its children, even when we huddle against the illusion of solidity on the ground beneath our feet. For millennia, humans have been both awed and unnerved by the void above. Before philosophy and science, early humans looked up and filled the darkness with stories of gods and heroes, of animals and spirits traced in the star patterns. These stories were our first attempt to make sense of the void, to tame its terror with imagination, and to express our awe. That human need for wonder has never left us. It merely found new forms. We still create stories of space, now with equations and telescopes, but also with dreams and art. Ancient philosophers pondered whether that void was truly nothing or filled with some invisible ether or celestial substance. To some, the night sky's darkness was sacred, the abode of gods or the shining realm of ancestors. To others, it was simply emptiness, terrifying in its boundless silence. We have peered up and wondered, what is the nature of that endless black? Is it mere emptiness between the stars? Or something deeper, a structure, a substance, an entity in its own right? As our understanding grew, we found that space is not an inert backdrop, but a dynamic, vital part of reality. It is not nothing at all. It has shape and structure, storms and whispers. It can bend and ripple. It erupted into existence and may one day fade. It connects the smallest atom in our bodies to the farthest galaxy in the universe. Space is the distance between us, yet it binds us to everything. It is the silence between notes in a grand cosmic symphony. Without the silence, the music could not be. In the same way, without the vast quiet of space, The brilliant fires of stars and the whirling patterns of galaxies could not exist or be perceived. Space holds time, matter, and even thought, an infinite stage where every story, including our own, unfolds. Already, we can sense that in exploring space, we are exploring ourselves as well, our origins, our essence. Think of the ground we've covered, space as a void and as a fabric. Its birth in the Big Bang, the quantum flickers in emptiness, the bending of starlight and the warping of time, the colossal structure of galaxies, the enigmas of dark matter and dark energy, the mysteries of black holes, the faint horizon of what we can see, the bravery of human explorers, and the tenderness of our consciousness nestled in a cosmic cradle. Each theme connected, forming a tapestry of understanding. Now, in that spirit, let us embark on this journey from the birth of the universe to the far future, from the smallest quantum flickers to the grandest clusters of galaxies. Let the story begin, as it always has, in darkness. But space was not always as we know it now. There was a time, if time is even the right word, when space itself was nowhere and nothing. In the beginning, there was not even emptiness, for there was no space to be empty, no distance, no outside or inside, no before or after. All that would become the universe was concentrated in an unimaginably small, hot point. In that primordial state, the seed of everything was contained in something infinitesimal, where the distinction between here and there meant nothing, because there did not yet exist. Then a flash, a furious expansion, an event we call the Big Bang. It was not an explosion in space, it was an explosion of space. Space itself unfurled from that first moment, swelling like a new blown bubble. In the first fractions of a second, the universe grew from smaller than an atom to larger than a galaxy. It was a blooming of space-time, a rush of creation so extreme our minds struggled to picture it. Time and space came into being together, intertwined from the start. In that instant of Genesis, energy roared forth, blazing light filled the young cosmos, and the very fabric of reality began to stretch. Try to imagine it. All of space compressed into a point and then suddenly expanding outward. There was no center in the usual sense. Every point in the nascent universe was the center, because the whole thing was expanding everywhere at once. The cosmos was incandescent, a churning plasma of particles and light. As space expanded, it cooled. In mere seconds, the hot broth of creation settled enough for the first protons and neutrons to form. Matter and antimatter were born in pairs, and almost all annihilated each other in flashes of gamma rays. But a tiny excess of matter, our future world, survived. In the next few minutes, those protons and neutrons fused into the first atomic nuclei. Hydrogen and helium, the lightest elements, formed in abundance as the fireball universe briefly became a nuclear furnace. Hundreds of thousands of years passed as the universe kept expanding and cooling. It remained blindingly bright, like the interior of a star, but that light was trapped in a dense fog of charged particles. Slowly, space grew vast and cool enough for electrons to settle into orbits around nuclei, forming the first atoms. Suddenly, the fog cleared. Light could travel freely across space for the first time, bursting outward as a great decoupling glow. That ancient light still washes over us today as a faint afterglow, a whisper from when the universe was newborn. Thus, space, once a pinpoint of fury, became an ever-expanding volume. Galaxies would coalesce billions of years later, but already the stage was set. Space had been born carrying time along with it. The distance between things began to grow, and with distance came the potential for structures, for motion, for cosmic evolution. The immense voids and stretches we now call space were initially tightly folded in that first moment. We are living in the aftermath of that expansion, Space is the legacy of the Big Bang, the arena inflated from that primordial flash. Every meter of empty space we traverse, every gap between star and star, was forged in that first event. In a sense, we are still inside the Big Bang, living in its cooling embers many eons later, as space continues to stretch around us. Now, as space grew and cooled, it might be tempting to think that truly empty space, pure nothingness, began to exist in patches where matter had yet to gather. But modern science reveals a profound paradox. Even the emptiest space is not truly empty. What we call a vacuum, devoid of atoms or light, is more like a restless ocean than a tranquil void. Imagine looking at a calm sea from afar. It appears flat and still, but up close you see incessant ripples and eddies. Similarly, what seems like pristine nothingness at the grand scale seethes with subtleties on the smallest scales. According to quantum theory, fields permeate all of space. Fields for electricity and magnetism, for gravity, for every kind of particle that can exist. These fields cannot be shut off. Even in a perfect vacuum, they retain a minimum energy, a jitter. Particles flicker into being from that energy and vanish almost immediately, like fleeting sparks in the dark. These aren't particles in the usual sense. They are virtual particles, born of uncertainty, living on borrowed time and energy, yet their effects are real. In the laboratory, if you place two metal plates extremely close together in a vacuum, the simmering vacuum energy between them changes and produces a subtle force pushing the plates together. The void exerts pressure. Nothingness has potency, so the void is full of potential. Empty space is more like a field of fields, all overlapping, invisible but present. Even when you remove every atom and every ray of light, space still retains this ground-level buzz of activity, a gentle quantum foam. This is sometimes called zero-point energy, the energy that remains when you take everything else away. It is staggeringly small in any tiny volume, yet because space is so vast, the collective effect of this vacuum energy might shape the cosmos. In fact, it could be related to the mysterious dark energy that is making the universe's expansion accelerate, an idea we will return to. In effect, the ancient notion of an all-pervading ether finds a new and unexpected echo. The fabric of space itself may be suffused with an exotic form of energy. Ponder that for a moment. The darkest, emptiest corner of intergalactic space, a million light years from the nearest star, still isn't truly empty. It contains the gravitational field stretching from distant masses, the ever-present field that endows particles with mass, and the jitter of quantum fields spawning ephemeral pairs. Space is like a silent symphony, where, even in the pauses between notes, a faint vibration hums. Nothingness, it turns out, is a sort of something. Philosophers long ago suspected as much, proposing that emptiness might hold hidden qualities. Here, science and philosophy meet. The vacuum is a paradox, a no-thing that is also a sea of energy and possibility, the blank canvas that is never truly blank. This paradox of nothingness gives us a new reverence for space. When we speak of the void, we now know it has structure and behavior. Empty space can bend and flex. It can carry waves, not sound waves, but gravitational waves, ripples in space-time itself. It can even spawn new space. Since the Big Bang, space has been stretching and generating more of itself. The emptiness that nature supposedly abhors is in truth rich and creative. In the vacuum of space, particles appear and disappear incessantly, and with them come forces and consequences. It is as though the universe, even when seemingly doing nothing at all, still whispers beneath the silence. The void is alive with the potential for everything. After all, it was out of an initial nothingness that the cosmos itself blossomed. From empty space sprang the fullness of the world, and even today, emptiness continuously lends reality its shape. Space, as we have seen, is far from a passive void. One of its remarkable properties is its ability to bend, warp, and curve in the presence of mass and energy. Gravity, which we experience as the attraction between masses, is in truth an expression of curved space and time. Massive objects distort the fabric of space-time around them, much like a bowling ball placed on a trampoline stretches and curves the surface. If you roll a marble near that bowling ball, the marble will spiral inward, not because the ball reaches out and pulls it, but because of the dent in the surface. So it is with planets orbiting stars and stars orbiting galactic centers. They are following the curves of space carved by gravity. Picture the space around the sun. The sun's great mass dents space into a kind of bowl shape. Earth is like a smaller marble caught in that bowl, perpetually rolling around the slope. We don't fall in because, in a sense, we are already moving sideways fast enough to circle around. Space guides our planet's path. Every object with mass does this, though usually the warping is tiny. You, right now, are bending space around you, but the effect is unimaginably small. A planet or star makes a noticeable curve, and near something as massive as a neutron star or a black hole, space-time curves dramatically, steepening into a deep well. This idea that gravity is geometry revolutionized our understanding of the cosmos. It means that space is elastic, shapeable. It can be stretched, as in the expansion of the universe, and it can be curved by mass. Space and time are woven together, so when space bends, time does too. A clock deep in a gravitational well, say on the surface of a dense planet, will tick a bit more slowly than a clock far out in space, where space-time is less distorted. Even light, which has no mass, feels the influence of curved space. It travels in what we perceive as a bent path when it passes near a massive object. We have seen starlight curve around the sun during eclipses, and distant galaxies appear distorted into arcs by the gravity of intervening galaxy clusters acting as cosmic lenses. Space is not a rigid backdrop. It is a flexible, active player in the cosmic drama. When massive objects move suddenly, imagine two black holes spiraling together and merging. Space itself can ring like a drum. Waves ripple outward at the speed of light. These are gravitational waves, faint tremors in the fabric of space-time, spreading across the universe. They are extremely subtle. By the time they reach us, they stretch and squeeze distances by less than a fraction of an atom. Yet with delicate instruments, we have detected these ripples, listening as black holes billions of light years away collide. In those moments, space carries a form of music. Not sound, there is no air in space for sound, but a gravitational melody that we can hear with the right instruments. It is a reminder that even in silence, there can be vibration and song. So gravity is the shape of space and time. Everything with mass tells space how to curve. The shape of space tells matter how to move. This intertwined dance means that space is almost like a fabric, dynamic and alive. A heavy object makes an indentation. A moving heavy object can send ripples. On Earth, we are rarely aware of this truth because we live in the same curved space as our planet. Like ants on that curved trampoline, we don't directly see the dent from our perspective, but we feel it as the force that keeps our feet on the ground. When we launch a rocket, we are essentially giving it enough speed to climb out of the curved well of Earth's gravity. Once in the gentler slopes of space away from Earth, a spacecraft can coast, looping in the broader, shallower curve of the sun's gravity. In the vacuum of space, light races at the fastest speed possible, about 300,000 kilometers per second. Even so, the universe is so vast that this incredible speed has its limits. Light takes time to travel, and thus as we gaze out into space, we are also looking back in time. This is one of the most profound realizations in astronomy. Distance in space is literally distance in the past. When you look at the moon, You see it as it was about 1.25 seconds ago, because that's how long its reflected sunlight takes to reach your eyes. When you watch the sun dip below the horizon at sunset, the sun has actually already set 8 minutes earlier. Its last rays are just now arriving. Extend this further. The light from the nearest star system, Alpha Centauri, started on its journey over 4 years ago. The glow of the Andromeda galaxy, faintly visible on a dark, clear night as a hazy smudge, left that galaxy more than 2 million years in the past, when early humans were just beginning to walk upright on Earth. And the light from the most distant galaxies we can see started its journey billions of years ago, long before the Earth itself existed. Space is a time machine. The deeper we peer into space, the further back in time we see. In the darkness overhead is a kind of layered record of history. Nearby stars showing recent centuries of their past. Distant galaxies offering a view of epochs long gone. The most distant light of all, the cosmic microwave background, is the afterglow from the birth of the universe itself, now stretched and cooled to a faint whisper in microwaves. That light has been traveling for nearly the entire age of the universe, almost 14 billion years, only now reaching our telescopes. When we capture it, we are capturing a baby picture of the cosmos, a portrait of space when it was only 380,000 years old. This means that when we study the universe, we must reconstruct events like archaeologists. We cannot see the universe as it is in this exact moment everywhere, only as it was when the light left each region. In a real sense, the night sky is full of ghosts, the images of stars that may no longer exist, the echoes of supernovae that exploded eons before humans learned to make fire. Yet these ghosts are our guides. By reading the faint light, with its colors and patterns, we uncover the story of galaxies and stars. The redshift of a distant galaxy's light, stretched to longer wavelengths by the expansion of space during its journey, tells us how far that light has traveled, and thus how long ago it started out. Thus, we piece together the chronicle of the cosmos, seeing chapter by chapter of the past. Powerful telescopes today can see galaxies that formed when the universe was only a few 100 million years old, a small fraction of its current age. With each technological leap, from the first ground-based spyglasses to space observatories that see infrared glimmers of the earliest stars, we extend our vision and push deeper into time. Recently, a new generation of telescopes has begun to reveal galaxies taking shape just a couple of 100 million years after the Big Bang, challenging our models of early cosmic history and showing that the universe may have built structures faster than we thought. Surprises like these remind us that space still holds many secrets waiting to be discovered. Our cosmic story is continually refined with each new observation. It is often said that to look into space is to look into our origins. Because light needs time to travel, the farther out we observe, the closer to the Big Bang we approach in time. We are essentially observing the cosmic dawn, the first generation of stars igniting and the first galaxies assembling. We stand on our tiny world, collecting ancient photons that have crossed the gulf of space for eons, and from them, we learn what happened long before we came to be. There is a quiet poetry in this. The darkness of space is not just an absence of light, but a vault of ancient memories, waiting to be seen by those with eyes to see and minds to understand. In contemplating the vastness of space and the finiteness of light's speed, one begins to grasp the tremendous scales involved. The universe's stretches are almost beyond imagination. But one way to feel the magnitude of cosmic emptiness is to compare it to the emptiness we carry within ourselves, within the atoms that make up our bodies. Every atom is mostly space. If an atom were enlarged until its nucleus was the size of a marble, the atom's outer edge, where the electrons roam, would be nearly as large as a football field. The nucleus sits tiny and heavy at the center, and the electrons are like distant motes buzzing around the edges. The vast majority, over 99.9999% of the atom's volume, is empty space. That means the solidity we feel, this page, your hand, the ground, is an illusion created by electromagnetic forces in what is otherwise void. You, me, the rocks and trees. We are built of tiny solar systems of emptiness with infinitesimal specks at the core. The distance between those specks and their electron clouds, relative to their size, is enormous. Emptiness is woven into matter itself at the smallest scales. Now scale up. The Earth orbits the Sun at about 150 million kilometers away, a distance so great that light itself takes 8 minutes to cross it. Yet on the scale of the solar system, that is a modest gap. Our solar system is mostly empty space. If the Sun were a ball the size of a grapefruit, Earth would be a tiny pebble orbiting about 15 meters, 50 feet away. Jupiter would be another marble dozens of meters out. And beyond Neptune, the farthest major planet, lies a stretch of space so large and sparse that the mind reels. Vast cometary clouds, extending perhaps a quarter of the way to the nearest stars, containing only thin dust and ice fragments drifting in the dark. The nearest star beyond our Sun is so far that analogies barely do it justice. If the Sun were that grapefruit in your city, the closest star would be another grapefruit thousands of kilometers away, perhaps on another continent. In between would lie nothing but the darkness of interstellar space. Maybe a few stray molecules, the odd dust grain, but essentially vacuum. This gulf between stars is typical in our galaxy. Though the Milky Way is a city of hundreds of billions of stars, each star is light years from its neighbors. A light year is about 9.5 trillion kilometers, or nearly 6 trillion miles. Even a beam of light needs years to go from one star to the next. Our galaxy is about 100,000 light years across, a staggering expanse where, even at light speed, it would take 100 millennia to traverse from edge to edge. Between galaxies, the distances grow even more daunting. The Milky Way and the Andromeda Galaxy, our nearest large neighbor, are separated by about 2.5 million light-years of emptiness. If the Milky Way were the size of a dinner plate, Andromeda would be another dinner plate a few meters away. Two enormous disc-shaped systems, each with hundreds of billions of stars, drifting slowly toward each other through a sea of darkness. And beyond our local group of galaxies, there are immense voids where, for tens of millions of light-years at a stretch, not a single galaxy shines. True cosmic abysses nearly devoid of matter. The scale of separation in the cosmos is truly unimaginable. It humbles any human scale we know. Our minds evolve to comprehend the distance of a thrown spear or the walk to a neighboring village, not the gap to a neighboring galaxy. Yet here we are, straining our thoughts to encompass billions of light years. We invent metaphors, atoms like stadiums, stars like distant grains of sand, to bridge the gap between our everyday experience and these extremes. Even so, the reality remains staggering. Almost everything is space. The cosmos is a faint scattering of islands, stars, galaxies, in a vast ocean of nothingness. If you could compress all the matter of the universe together, eliminating the empty space, it would occupy a surprisingly small volume compared to the volume of space it currently fills. By volume, the universe is overwhelmingly void. This emptiness, however, is not a flaw or a waste. It is what allows room for structures to form without immediately colliding. It is what permits planets to orbit stars safely, stars to move in galaxies, galaxies to dance in clusters without constant destructive encounters. Space provides the breathing room for existence. The great gulfs between atoms prevent solid matter from collapsing in on itself. The light years between stars prevent gravitational chaos. The void between galaxies gives each galaxy the solitude to evolve its own magnificent form. The separations define the structures. The nothingness shapes the something. In this way, the distance between things is also the thread that connects them in the grand design of the cosmos. If we could pull our perspective even farther back, far beyond our galaxy, beyond our local cluster of galaxies, we would begin to discern a pattern in the arrangement of galaxies themselves. On the largest scales, the universe has a structure, a vast cosmic web. Galaxies are not scattered randomly like grains of sand tossed on a floor, but rather arranged along filaments and clumped in nodes, with huge voids between them. Imagine a three-dimensional spider web, or the filigree of frost on a window pane, or the neural connections in a brain. The universe's galaxies trace similar patterns. There are regions where hundreds or thousands of galaxies cluster together in a knot, connected by long filaments of galaxies stretching outwards. Between these filaments lie enormous voids, spherical or elongated regions, spanning tens of millions of light-years, that contain only a few galaxies or none at all. This is the cosmic web, the large-scale skeleton of our universe. How did this web form? In the early universe, matter was almost uniformly spread, with tiny, denser spots and slightly emptier spots. Over billions of years, gravity amplified those slight differences. The denser spots grew denser as they pulled in matter from their surroundings. The emptier regions grew emptier as matter flowed out of them toward the denser attractors. With time, a foam-like pattern emerged. The densest seeds became clusters of galaxies. Matter flowed along filaments into these clusters, like rivers feeding lakes. The voids in between emptied out more and more. We ended up with this intricate structure, a lace of galaxy clusters and groups connected by bridges of matter, outlining cavernous voids where few stars shine. Intriguingly, this arrangement seems to be guided by an invisible hand. Dark matter. Dark matter, the mysterious substance that neither emits nor absorbs light, makes up the bulk of the matter in the universe, about 85% of it. It was dark matter's gravity that began the collapse of matter into filaments and nodes. Simulations of the universe's evolution, when they include a vast halo of dark matter particles, show the emergence of a cosmic web strikingly similar to what large telescopic surveys observe. It is as though dark matter provided a hidden scaffolding, and ordinary matter, the gas that formed stars and galaxies, followed that scaffold, outlining it with luminous points. We have even caught glimpses of this web. Astronomers using giant telescopes have mapped the positions of galaxies by the millions, revealing filaments and voids across billions of light-years. In surveys, they have identified colossal structures like the Sloan Great Wall, a filament of galaxies about 1.4 billion light-years long, and vast empty regions like the Boötes Void, an enormous spherical gap, roughly 330 million light-years across, containing far fewer galaxies than expected. These names sound abstract, but they underscore how huge and structured our cosmos is. In one striking image, a faint bridge of hydrogen gas, illuminated by distant quasars, was observed stretching between galaxies in the early universe, exactly where models predicted a filament of the cosmic web. The pattern of filaments and voids has become unmistakable. Astronomers speak of this cosmic web as the most fundamental, large-scale structure of our universe. If you could travel magically fast and hover outside the universe, you would see this network glowing faintly. The clusters shining bright where hundreds of galaxies clump together, the filaments as luminous strands between them, and the voids as vast black hollows. It would look somewhat like a network of veins or the synapses of a giant mind, though on an inconceivable scale. This is the architecture of the cosmos, a tapestry woven from gravity and time, with dark matter as the loom. Where filaments intersect, galaxies gather. Where filaments stretch out, galaxies line up like pearls on a string. And in the enormous voids, we find nearly pure space, the closest thing to nothing that nature allows, bounded by the walls of this cosmic honeycomb. Even as gravity pulled matter into this cosmic web, Another process was at work on the grandest scales, the expansion of space itself. Since the Big Bang, space has been stretching, carrying galaxies with it like chips of wood embedded in a rising tide. In the early universe, this expansion was furious. Later it slowed, as the mutual gravity of galaxies tugged against it. One might imagine a fireball explosion that initially hurls shrapnel outward rapidly, then slows as debris feels drag or gravitational pull. For a long time, astronomers thought that gravity might eventually slow the expansion to a stop or even reverse it into a collapse. But to our surprise, the expansion never halted. In fact, it began to speed up. About 5 or 6 billion years ago, a time when our own sun was still young, the universe's expansion started accelerating. Distant galaxies began receding from each other faster and faster. Some force or energy woven into the fabric of space was overpowering gravity on cosmic scales. We call this mysterious agent dark energy. Its nature is one of the biggest puzzles in science today. We observe its effects. It makes up roughly 70% of the total energy content of the universe and is smoothly distributed throughout space, not clumped like matter. It acts as a sort of anti-gravity, a pressure inherent to empty space that pushes outward. One way to think of dark energy is as a property of space itself. As space expands, new space comes into being, and with it, more of this repulsive energy. It's as if the very fabric of the cosmos has an inbuilt tendency to stretch, a subtle springiness. This is why distant supernovae appear dimmer than expected. They are farther away than they would be in a universe slowing down. The light had to travel a greater distance, and thus time, because the space between here and there expanded more while it was en route. Multiple lines of evidence, from those supernova measurements, from the patterns imprinted in the cosmic background light, from the distribution of galaxies, converge on this truth. The expansion is accelerating under the influence of something invisible and pervasive. What is dark energy? We do not yet know. It could be the zero-point energy of the quantum vacuum we talked about earlier, the residual energy of empty space, scaled up to cosmic proportions. If that's the case, it is essentially Einstein's cosmological constant come to life, a constant energy density filling space. Or dark energy might be a new kind of field, a dynamical energy that changes over time, sometimes called quintessence. Some even speculate about exotic possibilities. Perhaps dark energy hints that our understanding of gravity is incomplete on the largest scales, or that our universe interacts in subtle ways with others. These ideas remain speculative. For now, dark energy behaves, as far as we can tell, like a constant. A steady background push making the universe expand faster and faster. So what does this mean for the future? If dark energy remains dominant and roughly constant, the universe will keep expanding faster indefinitely. Over immense times, galaxies outside our local group will slip beyond our cosmic horizon, their light stretched and weakened until they effectively disappear from view. The night sky will, in the extremely far future, grow emptier as only the closest galactic neighbors remain visible. Dark energy is like a gentle yet inexorable wind pushing the cosmic web apart. It fights against gravity's effort to congregate matter, and on the largest scales, it wins. The ultimate fate of the cosmos depends on dark energy's nature. Will this acceleration continue forever, leading to an ever colder, lonelier universe? The data so far suggest yes, though we cannot be entirely certain. Some speculative scenarios. If dark energy were to grow in strength over time, a doomsday scenario dubbed the Big Rip, eventually even galaxies, stars, planets, and atoms could be torn apart, billions of years hence. Conversely, if dark energy is not perfectly constant but decays, the expansion might slow or even halt in the far future, perhaps leading to a cosmic turnaround or collapse, Big Crunch. Right now, Evidence points to dark energy being consistent with a constant energy of space, meaning a slow drift toward an ever sparser cosmos, sometimes called a heat death. But these are far future possibilities, tens of billions or trillions of years ahead, far beyond human timescales. In any case, the discovery of dark energy in the late 20th century was a humbling reminder that space holds secrets far beyond our reckoning. Just when we thought we understood the grand motions of the cosmos, the universe unveiled a new twist. The expansion can accelerate, driven by a hidden energy in the void. Space, once again, proved to be not passive emptiness, but an active agent with its own properties and dynamics. We have spoken of dark matter's role in shaping the cosmic web. But dark matter's influence is equally crucial on the scale of individual galaxies and clusters. It is often called the universe's silent majority, unseen yet dominant in mass. While dark energy governs the universe's expansion, dark matter governs the clumping of structures within it. When we look at a spiral galaxy like our Milky Way, we see a rotating disk of stars, gas, and dust. The visible stars amount to only a small fraction of the galaxy's mass. We know this because of how the galaxy rotates. Stars in the outer parts of the Milky Way orbit the galactic center much faster than they would if only the visible matter's gravity held them in. If we count just the stars, gas, and dust that we can see, the outer stars should drift away, unable to hold on at such speeds. Yet they remain bound, as if an enormous hidden mass is providing the extra gravitational pull. That extra mass is dark matter. Dark matter surrounds galaxies in a vast halo extending well beyond the visible edge. In our galaxy, the luminous disk of stars is maybe 100,000 light-years across, but the dark matter halo might span 600,000 light-years or more. This halo is roughly spherical, perhaps slightly squashed, enveloping the galaxy like an invisible cocoon. It's sparsest at the edges and densest toward the center, but even in the center, dark matter passes through ordinary matter almost ghost-like, rarely interacting except through gravity. Thus, every galaxy sits in the heart of a heavy, unseen cloud of dark matter. The stars are like dust caught in a gravitational well created by this invisible mass. We cannot see dark matter directly. It emits no light, no radiation we can detect. We infer its presence solely from its gravitational effects. Beyond galaxy rotation speeds, another strong piece of evidence comes from clusters of galaxies. Clusters are collections of hundreds or thousands of galaxies bound together. Observations as far back as the 1930s noted that galaxies in clusters move too rapidly to be held together by the gravity of visible matter alone. Later, X-ray observations found that clusters are filled with extremely hot gas, which itself outweighs the visible galaxies. Yet even gas plus galaxies wasn't enough to explain the gravitational glue. Again, dark matter provided the answer. Furthermore, clusters, and even galaxies, act as gravitational lenses, bending and distorting the light from background galaxies into arcs and rings. By analyzing these lensing patterns, we can weigh the cluster and map where the mass lies. These maps invariably show far more mass than can be accounted for by luminous matter and distributed in a diffuse halo. In some famous cases, such as the Bullet Cluster, the collision of two galaxy clusters, we see that the stars of the clusters pass through each other relatively unscathed. The hot gas slammed into each other and slowed, giving off X-rays. But the bulk of the mass, inferred from lensing, sailed through with the stars. This suggests the dark matter did not collide like the gas did. It passed through, interacting only via gravity. It's a cosmic demonstration that dark matter is a distinct component, not just hidden ordinary matter. What is dark matter? Much like dark energy, it remains unknown in composition, though its behavior is less exotic in many ways. It clumps under gravity, for instance. It could be a new kind of particle, perhaps something like an invisible cousin of the neutrino, a particle that rarely interacts. Experiments deep underground and in space are trying to catch the faintest whispers of dark matter particles streaming through Earth. So far, they have only narrowed the possibilities, not conclusively found them. Another clue comes from the early universe. Subtle patterns in the cosmic microwave background and the abundances of light elements tell us dark matter is not made of protons and neutrons, baryons, the stuff of atoms, but something else that did not interact with light or normal matter in the early hot universe. For now, dark matter remains a silent partner. It neither shines nor blocks light, but it shapes the universe on every level. Without it, galaxies as we know them might not have formed or might fly apart. With it, they coalesced and hold together. Our own existence likely owes to dark matter's stabilizing gravity. Without the enormous hidden halo of the Milky Way, our galaxy's spinning disk might not have stayed intact for billions of years, for life to develop in a stable environment. This ghostly matter is almost a spiritual presence in a scientific sense. Omnipresent, yet invisible, influential, yet elusive. One cannot help but feel a sense of mystery and respect, knowing that when we look out at the night sky, most of the mass shaping the glittering patterns of stars and nebula is invisible to our eyes. Among the most startling outcomes of gravity's ability to warp space are black holes, regions where space turns so steeply inward that not even light can climb out. Black holes are space gone rogue. Gravity run amok to the point that a massive star's core, or any sufficiently dense mass, collapses virtually to a point. They are the graveyards of massive stars, and perhaps the seeds of new cosmic structures. In a sense, black holes are where space itself falls inward, dragging anything nearby with it. Imagine a star many times heavier than the Sun, burning its nuclear fuel fiercely over a few million years. Eventually, the fuel runs out, and the core collapses under its own weight. If the star is massive enough, more than about 20 times the Sun's mass initially, no force in the universe can halt that collapse. The core implodes. Electrons and protons crush together to form neutrons, as in a neutron star, but even neutron pressure fails if the mass is too great. Gravity wins completely. The core continues collapsing past any known state of matter, and a black hole is born. All the star's mass is now contained in an infinitely small point, according to classical theory, at the center of a region of radically curved space. Surrounding that point is an invisible boundary called the event horizon, the point of no return. Once anything, matter or light, passes inside the horizon, it cannot escape back out. To an outside observer, the event horizon is essentially the black hole's surface, though it's not a tangible surface. It's the radius at which escape velocity equals the speed of light. For a star-sized black hole, this horizon might be only a few kilometers across, even though it contains a mass several times that of the Sun. Imagine the Sun crushed down to the size of a city. That's the kind of density and curvature we are talking about. Inside the event horizon, space and time themselves trade roles in a strange way. Falling towards the center is as inevitable as moving forward in time. All possible paths lead deeper in. What lies at the very center? General relativity says a singularity of infinite density, but in truth, our physics breaks down there. Quantum gravity, the unification of quantum mechanics and gravity that we haven't solved yet, would be needed to understand it. Perhaps there is a tiny warped region, or even a bridge to elsewhere. Speculative ideas like wormholes have been imagined lurking in these depths, but evidence is lacking. From outside, what we see of a black hole is not the hole itself, which emits no light, but its effects on the surroundings. Gas spiraling into a black hole heats up and glows brilliantly in X-rays just before crossing the horizon. If the black hole is feeding, we often see an accretion disk of superheated matter and sometimes jets of particles shooting out at nearly light speed from the poles, powered by the hole's magnetic and rotational energy. But the clearest signature is gravitational. We observe stars orbiting an invisible mass, as in the center of our own Milky Way, where stars whip around a dark center at thousands of kilometers per second, indicating a mass 4 million times that of the Sun confined in a space smaller than our solar system. Nothing but a black hole could do that. Indeed, we are now certain that a supermassive black hole anchors most, if not all, large galaxies, including ours. Only recently, humanity captured its first image of a black hole's immediate vicinity, a glowing donut-shaped ring of light surrounding a dark shadow in the core of galaxy M87, about 55 million light-years away. This shadow was the silhouette of the event horizon's influence, the closest we can come to seeing the unseeable. It affirmed that our concepts of these cosmic abysses are not mere math fiction. They are real. Black holes come in different sizes. Stellar black holes form from collapsing stars and weigh a few to dozens of suns. Supermassive black holes, millions to billions of solar masses, reside in galactic centers. They likely grew by consuming stars and gas and merging with other black holes over billions of years. We've even found middling black holes, intermediate mass, and speculate tiny primordial ones might have formed in the early universe. Despite their fearsome reputation, black holes are not cosmic vacuum cleaners, indiscriminately sucking everything in. An object can orbit a black hole safely from a distance, much as it would orbit any mass. Only when you venture too close, within the horizon, is escape impossible. However, the extreme environment near a black hole can shred stars via tidal forces and power those spectacular jets and high-energy radiation that can stream outward for thousands of light-years. Black holes push physics to its limits. They represent space curved to an extreme and time slowed to a crawl at their threshold. If you watched a clock falling toward a black hole, you'd see it tick slower and slower as it neared the horizon, never quite appearing to pass through. It would fade and redshift to darkness. Meanwhile, the clock itself, were it indestructible and could fall in, would experience time normally and cross the horizon without fanfare, only to meet whatever fate awaits inside. It's as if the fabric of space-time gets so warped that it pinches off a region from causal contact with the rest of the universe. That pinched-off region is the black hole's interior, a kind of cosmic oubliette, a place where information goes in and, according to our best understanding, cannot come out. This raises deep questions about the nature of information in physics, the black hole information paradox, which physicists are still debating. In addition, theory predicts that black holes aren't completely black. They can emit a very faint glow of particles due to quantum effects at their horizon, a phenomenon called Hawking radiation. Over mind-boggling spans of time, black holes can slowly evaporate by this process, one trickle of radiation at a time. A black hole the mass of the Sun would take far longer than the current age of the universe to evaporate. So this effect is negligible for now, but for the smallest black holes it could be significant. It ties into the information paradox as well. If black holes eventually vanish, where does the information about what fell in go? Does it come out in the Hawking radiation in scrambled form? These questions show how black holes force us to unite principles of quantum mechanics and relativity in our quest for answers. Thus, black holes sit at the intersection of the cosmic and the quantum, teaching us about gravity, thermodynamics, and the limits of knowledge. In a more poetic sense, black holes are like the universe contemplating its own depths. They are the night within the night, a darkness so absolute that it challenges our notions of space and existence. They remind us that space can fold in on itself and create edges to reality, boundaries beyond which we cannot see or know. They are not just holes in space, but holes in our understanding, calling to us with mysteries. And yet, they are also integral to the cosmos. By merging and growing, they release energy and shape galaxies, perhaps even triggering new star formation via their outflows. Even in their silence, they influence the grand design. Space, turned inward upon itself, creates these paradoxical objects where end and beginning blur. In the vicinity of a black hole, one truly feels that the line between nothingness and something has thinned to its limit, a fitting extreme in our journey through the realms of space. For all the wonders that fill space, there is a fundamental limit to how much of the universe we can see or ever influence. We call this limit the observable universe, the sphere around us, beyond which light has not had time to reach us in the almost 14 billion years since the Big Bang. It's as if we are inside a glowing bubble, where the glow marks the farthest things we can observe. Beyond that horizon, there may be more galaxies, more space, perhaps an infinite expanse, but they are, for now, and likely forever, out of reach. This cosmic horizon exists because the universe is finite in age, and light has a finite speed. Think of standing in a vast plain shrouded in fog. You see a circle around you up to a certain distance where the fog becomes opaque. You suspect the plain continues beyond, but you cannot see it. Our cosmic fog is simply the fact that beyond a certain distance, light hasn't yet arrived, or has been stretched and dimmed beyond detection. At the edge of our vision lies that afterglow of the Big Bang, the cosmic microwave background, which acts like a bright wall of light from 380,000 years after the universe began, beyond which we cannot see with light, because earlier the universe was opaque. That shell of light is currently about 46 billion light-years away in all directions, much farther than 13.8 billion light-years, because space itself expanded while the light traveled. That defines the radius of our observable universe. It is humbling to realize that no matter how advanced our technology becomes, we cannot obtain information from beyond our cosmic horizon by any normal means. Those regions are not just far away in space, they are effectively unreachable in time. Their light may only arrive far in the future, or perhaps never, if cosmic expansion carries them away faster than light can bridge the gap. In an accelerating universe like ours, there are galaxies right now on the edge of visibility that will eventually fade away as well. The horizon of our observable universe can, in fact, shrink in terms of what remains visible in the far future. This means our observable universe is a dynamic thing. Over cosmic time, new regions become observable as their light finally arrives, while very distant regions slip beyond view. However, from our standpoint today, we have a vast observable universe to explore with our minds. It contains an estimated 2 trillion galaxies, each with billions of stars. Within the 93 billion light-year diameter sphere, we can, in principle, observe. That number boggles the mind, yet it might be only a small fraction of the whole universe if space extends far beyond what we can see. We must accept that there is a horizon to our knowledge, an edge beyond which we cannot peek, at least not with light or signals as we understand them. The existence of this horizon also reminds us that our place in the universe is not central in a spatial sense. Every observer, wherever they are, has their own observable bubble of similar radius centered on them. An alien in a galaxy billions of light-years away sees its own cosmic microwave background and horizon, overlapping with ours in some regions, but including parts of the universe we cannot see and excluding parts we can. It's a bit like being in the middle of an ocean. You see the circle of the horizon around you, but you know the ocean continues beyond. We float in the cosmic ocean, seeing a sphere of sky around us, but the cosmic ocean itself likely stretches well past that boundary. Sometimes, in our imaginations, we wonder, what lies beyond that horizon? More galaxies receding forever? Perhaps parts of the universe with different properties? Or simply an endless stretch of more darkness and light? We don't know, and perhaps cannot know. Yet we can be grateful that we can see as much as we do, a glorious expanse of space and time, nearly 14 billion years deep. Within that volume, we have uncovered physics that likely applies everywhere beyond as well, giving us confidence that the unseen parts follow the same cosmic story. Our observable universe defines the stage of our cosmic story. It is enormous, yet finite from our perspective. Beyond its curtain lies mystery. This horizon of visibility is a gentle reminder of our limitations. It tells us that no matter how much we strive, there will always be something just out of reach, a frontier that recedes as we chase it. And perhaps that's for the best. An infinite universe with finite observation keeps us always wondering, imagining, and pushing to understand what might lie beyond the next horizon. Now, let us drift away from all these structures, beyond the warm lights of galaxies and the faint gauze of clusters, into the great dark in between. This is intergalactic space, the expanse between galaxies. Here, in the middle of a vast cosmic void, you would find yourself in nearly perfect silence and solitude. No nearby stars, no nebulae, likely not even a single atom in the volume of your body. The nearest galaxy might appear as just a tiny smudge of light, or perhaps nothing visible to the naked eye at all. You are as alone as one can be, surrounded by a blackness almost undisturbed by any glimmer. This is the closest thing to nothingness the universe offers on a macro scale. Intergalactic space is not completely empty, but it comes impressively close. In the most rarefied voids, there may be only a handful of atoms in an entire cubic meter of space. Imagine an area the size of your living room containing perhaps a few stray hydrogen atoms and maybe a single photon passing through. For all intents and purposes, it is a vacuum better than anything we can create on Earth. No sound can travel here. Sound requires a medium like air or water, and here there is effectively none. If you were somehow alive and unprotected in this environment, setting aside the impossibility of no air and extreme cold, you could scream, and no one would ever hear even the faintest whisper. The concept of noise simply does not apply. It is a cathedral of silence. The darkness is equally profound. Far from any star, you would see blackness in all directions. Perhaps, if your eyes were sensitive enough, you'd catch the faint collective glow of distant galaxies as a weak background light, much like the Milky Way band appears from a dark Earth location, but far dimmer. And of course, the universe is filled with light of wavelengths our eyes cannot see. Infrared, microwave, radio waves, even the cosmic microwave background radiation permeating every inch of space at a temperature of 2.7 K, just above absolute zero. But to human senses, intergalactic space feels utterly dark. It's not the kind of darkness we find in any earthly night, where usually some starlight or airglow exists. It's a nearly perfect black, limited only by the faintest glow of faraway galaxies and that omnipresent microwave whisper. In this void, time itself marches on in isolation. A clock would tick just fine, in fact, slightly faster than on Earth, since it's far from any significant gravity, but nothing marks the time. Days and nights have no meaning without a nearby star. A human being would soon lose track of all sense of time, with no external cues, only the steady beating of their own heart, which too would eventually feel deafening in the absolute quiet. Intergalactic space can be thought of as the universe's great wilderness. Just as deserts and open oceans on Earth are sparsely populated, the cosmic voids are deserts of matter. Yet like those terrestrial emptinesses, they have a stark beauty and significance. They are the canvas on which galaxies are arranged. Their emptiness defines the walls of the cosmic web's rooms. They also contain mysterious cosmic rays and tenuous gas that, while incredibly dilute, stretch over enormous volumes and over cosmic time, can influence galaxies when that gas slowly drifts into them or gets ignited by shocks. And though seemingly void, this space is crossed by intangible messengers. Neutrinos emitted by distant supernovae zip through these voids, hardly ever interacting with anything. Gravitational waves pass by, distorting distances by tiny fractions as they go, unimpeded by the lack of matter. The void is the highway of light and gravity across the cosmos. It is the medium through which information of cosmic events travels. One might say that even in emptiness, there is connection, an invisible thread of forces and particles in transit, binding the cosmos together, however tenuously. The emotional weight of such loneliness is hard to fathom. When we send spacecraft out beyond Pluto into interstellar space, which is still far denser than truly intergalactic space. We marvel at them entering deep space, but even they are still within our sun's sphere of influence, surrounded by traces of the solar wind. True intergalactic space lies far beyond, where the influence of any single galaxy is faint. It is a stark reminder of the vast separation the universe imposes between islands of matter. If one were to travel between galaxies, centuries or millennia of traversing nothing await. Yet this nothing is not frightening in the cosmic perspective. It's peaceful and sublime. It's the backdrop that makes the bright islands of stars all the more precious and brilliant. In the great cosmic voids, one confronts the reality of a universe mostly made of darkness and silence. But instead of seeing it as bleak, we might see it as serene. It is the quiet on the canvas that allows the lights of galaxies to stand out. It is the stillness that lets the song of creation, the stars and galaxies and life within them, be heard. The isolation of intergalactic space also carries a philosophical lesson. We, living on a cozy planet in a bustling solar system in a sprawling galaxy, are sheltered from this extreme loneliness by layers of structure and community in the cosmos. We have the warmth of our sun, the protective bubble of our heliosphere, the gentle glow of the Milky Way in our night sky. Only when we venture far beyond do we find the true void. It is out there, immense and indifferent. But from that emptiness, we also came, and to it, if we journey far enough, we return, carrying the spark of life into the dark and filling the void with meaning by our presence. Up to now, we've spoken much of space, the vast distances and structures, the emptiness and connections. But space has an inseparable partner, time. Together they form the fabric of space-time. And just as space is not absolute or fixed, neither is time. The flow of time can stretch, bend, and even nearly stall under the right conditions, intimately entwined with space. Modern physics has revealed that time is relative. A moving clock ticks slower than a stationary one from the stationary perspective, and a clock deep in a gravitational field ticks slower than one in open space. This isn't just theory, it has been measured. Time dilation is a daily consideration in technologies like GPS satellites high above Earth. They tick a bit faster due to weaker gravity and a bit slower due to their high speed. And both effects must be accounted for so that navigation on Earth remains accurate. Consider a scenario. Twins, one stays on Earth, the other takes a fast spaceship to a distant star and back. Upon reuniting, the traveling twin will have aged less than the twin who stayed behind. Perhaps the traveler experienced only 5 years while 10 years passed on Earth. This is not science fiction, but a result of the geometry of space-time. High-speed travel makes the traveler's path through time lean more towards space, distance traveled, and less through time, so to speak. They age less. This is called time dilation due to motion, special relativity, and it has been confirmed with subatomic particles in accelerators and with precise atomic clocks on fast jets. Similarly, imagine a clock at the top of a mountain and another at sea level. The clock at sea level, deeper in Earth's gravity, will tick slightly more slowly than the one at altitude. This gravitational time dilation has also been measured. It's tiny for Earth's gravity, nanoseconds of difference, but near something like a neutron star or black hole, it becomes dramatic. If you hovered just outside a black hole's event horizon, your time might be so slowed relative to the outside universe that a few minutes for you could equate to years or centuries passing for distant observers. This scenario, though exaggerated, was popularized in fiction, but it's grounded in real effects. What does it mean that time can bend? It means that simultaneity, what events happen at the same time, is not universal, but depends on motion and gravity. It means that cause and effect can get tricky if one isn't careful with reference frames. Yet, the speed of light and the structure of space-time preserve a causal order. Nothing can go back in time to create a paradox, as far as we know. It simply changes our intuitive Newtonian idea that time flows equably for all. Instead, each observer carries their own clock, and that clock's readings depend on the observer's path through space-time. Even our everyday life experiences a touch of this. Someone living at high altitude ages a few microseconds faster over a lifetime than someone at sea level. Astronauts orbiting Earth at 28,000 km/h experience time a tiny bit slower due to speed and a tiny bit faster due to being higher up, less gravity. The net effect is they age just a hair less than people on Earth. After a year in orbit, an astronaut might be milliseconds younger than an Earth-bound twin. Imperceptible, but real. Time is sometimes visualized as another dimension like space. Just as one can walk different routes through space, one can take different routes through space-time that result in different amounts of time experienced. However, unlike the spatial dimensions in which we can move freely, forward, back, left, right, up, down, time for us has a direction, ever forward. We can move slower through it, relative to others, by moving fast or hanging out in strong gravity, but we cannot turn around and go back. Space offers many possible paths, but time's arrow points one way for all of us, likely linked to the thermodynamic arrow, entropy increasing, that gives time its direction. The intertwining of time and space means that a curved clock is a reality. Clocks follow the curvature of space-time. Wherever space is warped, time is warped too. So a curved clock might be an image of a clock near a massive body being literally influenced by that warping. For instance, a clock on a satellite orbiting Earth is in slightly differently curved space-time than one on Earth's surface, and they diverge unless we adjust them. In essence, every massive object is like a slight break on time in its vicinity. We all live in the little dips in time created by Earth's mass, making our time run imperceptibly slower compared to far-off space. We don't notice because all our human reference points are similarly affected. Philosophically, this relativity of time can be both unsettling and awe-inspiring. It suggests that time is part of the physical fabric, not an immutable backdrop. It means the universe has a personal relationship with each traveler. Your time is yours, mine is mine, and they can differ, yet both are correct for each of us in our own frame. We carry our slice of space-time with us. And though we can't help but move forward in time, we have found ways to manipulate our experience of time by how we move in space or where we situate ourselves. In the cosmic context, understanding time's malleability allows us to navigate the universe more wisely. It tells us that extremely advanced spacefarers, if they ever exist, might exploit time dilation for long journeys, putting themselves in a slower time stream relative to home to make a long voyage more bearable subjectively. It also tells us that near black holes, time gets so bent that one could, in principle, see far into the future of the outside universe while only a short time passes for them, though retrieving that person would be another issue. Everywhere in space, time is quietly varying, slightly different on a mountain than in a valley, slower in Jupiter's gravity than in Earth's, slower still near the Sun. Our universe is a collection of all these personal times, woven together by light signals into a consistent tapestry, but each thread has its unique pace. When you next look at a clock, consider that its ticking is not absolute. Out in space, that same second might stretch or shrink depending on motion and gravity. Time flows like a river, but it can meander, speed up, or form eddies. This is part of the wonder of space-time, a medium so supple that not only can distances shift, but durations can too. Space holds time within it, as a melody holds rhythm, each shaping the other. Our journey through space and time so far has been one of the mind's eye. But there came a moment in our history when space stopped being only a concept out there and became a place we could physically touch. For eons, we were earthbound, looking up and dreaming. Only in the last brief blink of our existence have we reached our hands into the sky and felt the void beyond our world. the first steps were indirect. We built machines to fling into space. In the mid-20th century, a silvery sphere with small antennae was launched beyond the atmosphere, circling Earth. That first artificial satellite was humanity's opening note in the song of space. It carried no life, just a radio beacon, but it proved we could leave our cradle. Soon after, living creatures, and then humans themselves, rode fire and thunder to break the bonds of gravity. When the first person orbited Earth, they became a tiny moon to our planet, experiencing weightlessness and the black sky above our atmosphere. In those moments, space was no longer an abstract void, but a real place where a human heart could beat. Courageous explorers flew in cramped capsules and winged spaceplanes, trusting their lives to thin metal shells that separated them from deadly vacuum by mere inches. They saw with their own eyes the curvature of Earth against the black of space, and stars that do not twinkle, for there is no air up there to make them shimmer. Then came one of humanity's defining moments, setting foot on the moon. Our natural satellite, a piece of the cosmic neighborhood, was reached by human explorers. When they stepped onto the grey, dusty regolith, the boundary between Earth and space was profoundly crossed. For the moon is a world in space, with no air and an alien sky. Standing there, an astronaut saw Earth not beneath their feet, but hanging in the sky, a blue marble suspended in darkness. In that instant, space wasn't just something around us. It was the ocean in which two worlds, Earth and moon, floated, and a human stood on one looking at the other. The footprints left on the lunar surface are still there, undisturbed in the silent vacuum. They may last millions of years. In that sterile, airless environment, those prints are a message frozen in time. We were here. We came from another world. Meanwhile, we began populating near-Earth space with satellites of all kinds, for communication, for navigation, for studying Earth's weather and climate, and for peering out into the universe. Our planet became encircled by a shell of human-made moons, sending radio signals and digital information around the globe. At the same time, we built robotic probes to visit other planets, becoming our emissaries to places we cannot yet go ourselves. We sent orbiters and landers to the Moon, Mars, Venus, Jupiter, Saturn, and beyond. We have touched the surface of Venus with a lander, which survived only moments in its hellish heat, and of Mars with rovers that roam for years. We have even sent probes sailing out of the solar system entirely, carrying golden records etched with sounds and images of Earth, like a cosmic message in a bottle. To truly extend our senses, we also placed telescopes above our blurring atmosphere. These orbital observatories, free from the distortion of air, began to show us the cosmos in unprecedented detail. Famous space telescopes revealed star-forming nebulae as great cosmic landscapes, surveyed distant galaxies, and even measured the age of the universe with precision. They also looked back at Earth, underscoring how thin and precious our livable atmosphere is, and how alone our blue world seems against the black backdrop. Each telescope and probe is like a stretching of our nervous system into space, a way to feel and see beyond our natural reach. In low Earth orbit, we assembled a large space station, a habitable artificial world where, since the dawn of the 21st century, humans have lived continuously, conducting science and learning how to survive off-planet. This orbiting laboratory is a symbol of international cooperation and a beachhead for future space endeavors. Astronauts aboard see 16 sunrises and sunsets each day as they circle the globe every 90 minutes. They float in microgravity, adapt to an existence where up and down have little meaning. From their vantage, they see Earth as one borderless realm and space as an endless expanse beyond. They are inhabitants of the space between worlds, a small step toward living continuously in that frontier. Each of these achievements, satellites, moonwalks, space stations, interplanetary probes, space telescopes, is a thread stitching humanity into the fabric of space. No longer are we mere observers. We have become participants. We have left footprints on another celestial body, extended our eyes to the far reaches of the cosmos, and even sent objects beyond the solar system. We have touched space and been touched by it. Who can forget the poignant sight of Earth rising above the moon's horizon, or the breathtaking images of Saturn's rings backlit by the sun, or a deep field photograph showing a swarm of galaxies billions of years old in a patch of sky no bigger than a grain of sand? These moments expand our perspective, making space not just an abstraction, but a place we know, even if vicariously. We carry the dreams of past generations who gazed up in wonder, and we prepare the way for future generations who will go farther still. Leaving Earth, even temporarily, changes a human being. In microgravity, the near weightlessness of orbit, astronauts experience both wondrous freedom and profound physical challenges. Their bodies, evolved over millions of years to work against gravity's pull, must adapt within days to its near absence. This adaptation is fascinating and instructive, showing how intimately we are tied to Earth's environment and how we might adjust to new ones. One of the first things astronauts notice is the relief from weight. They can lift heavy equipment with a fingertip, float effortlessly from one end of their spacecraft to the other. It's like an endless dance or flight. Many speak of the joy of drifting, the childlike play of somersaults in mid-air. But microgravity also causes bodily fluids to redistribute. Blood and water that are normally pulled to our legs by gravity now move upward. Faces become puffy, legs slim. Astronauts often feel congested, as if hanging upside down. This fluid shift can also alter eye shape and pressure, causing some to need glasses in orbit or have vision changes that sometimes persist after return. Without gravity's constant tug, bones and muscles no longer bear weight. As a result, they begin to weaken. We have learned that astronauts can lose 1 to 2% of their bone density per month in space, especially in weight-bearing bones like hips and legs, an extreme, accelerated osteoporosis. Muscles, too, atrophy, particularly the postural muscles that help us stand upright. To counter this, astronauts must exercise vigorously for a couple of hours each day using resistance machines and cycling or treadmill devices. They often must be strapped down so they don't float away while running. Exercise helps reduce the loss, but some bone thinning and muscle shrinkage still occur. After a long mission, astronauts return to Earth temporarily weaker, and it can take weeks or months of rehab to rebuild what was lost. Interestingly, astronauts often grow a bit taller in space, by a few centimeters, because without gravity compressing the spine, the vertebrae separate slightly. They enjoy being taller for a while, but this can also cause back pain as the muscles supporting the spine must stretch differently. The heart, not having to pump blood uphill from the feet as much, can weaken and change shape slightly. It becomes more spherical and may decrease in volume output. The longer-term effects of this are still being studied. Also, the balance system in our inner ears, which uses fluid and tiny hairs to sense orientation, gets confused without a gravity reference. Many astronauts experience space adaptation syndrome, motion sickness, for the first couple of days, nausea, dizziness, as their brains recalibrate to a world where down is no longer meaningful. Once adapted, their vestibular systems essentially tune out the gravity reference, and they move quite adeptly in 3D, able to work on any wall or ceiling as easily as a floor. Living in confined quarters for months poses psychological and social challenges as well. Astronauts miss weather, rain, wind, the feeling of sun on skin. They have sunlight through windows, but not the breeze. They miss certain foods. Fresh fruits and vegetables are a delicacy when supply ships arrive. They are extremely busy, which helps, but they're also isolated from normal life, with only emails or occasional video calls home. The camaraderie with crewmates and the sense of mission help keep them mentally healthy. But every astronaut feels the absence of Earth in subtle ways. The smell of soil and trees, the sound of birds, the presence of family. It is the sacrifice they make to push into the frontier. Yet, there are profound positive transformations as well. Many astronauts describe the overview effect, a cognitive shift when seeing the whole Earth from space. They see our planet as one borderless orb, fragile and beautiful against the black void. This often instills a deep sense of interconnectedness and a desire to protect our home world. Some speak of it in spiritual terms, a near transcendent experience of seeing Earth in its entirety and realizing the unity of humanity and the thinness of the atmosphere. This perspective shift is a psychological transformation unique to spacefarers, and it is considered one of the most powerful effects of space travel on the human mind. On the space station, astronauts also carry out tasks that change their relationship with mundane things. They learn to eat by chasing floating blobs of water or juice and capturing them in their mouths, or by carefully sticking their food packages to surfaces with tape so they don't drift away. They sleep in sleeping bags tethered to a wall or ceiling, enveloped so they won't float and bump into equipment. Some say sleeping in microgravity, without a mattress pressing against you, feels like curling up in mid-air. Odd at first, but eventually comfortable, like being cradled by space itself. They also find that their sense of time can shift. With 16 sunrises a day, they rely on clocks and scheduled night periods with window shutters closed to simulate day-night cycles for their body's rhythms. Over longer durations, the question arises, could the human body adjust more permanently to microgravity or partial gravity, like the 0.38 g on Mars? Would children born in such environments develop differently? We have some data from astronauts spending a year or more in orbit, which show that extended microgravity largely continues the same trends of bone loss and muscle adaptation, eventually reaching a new lower equilibrium. The body is resilient and adapts impressively, but certain systems like bone might not fully recover if the duration is too long. We don't yet know the limit. We do know that radiation exposure in space, outside Earth's protective magnetic field, poses serious health issues for longer voyages, as cosmic rays slowly damage cells and increase cancer risk. Future spacecraft and habitats will need better shielding and perhaps medical countermeasures to mitigate this. Perhaps, over centuries, humans living on Mars or other worlds would gradually develop new traits. Taller frames in low gravity, denser bones to resist bone loss, altered circadian rhythms to match their world's day length. They might become somewhat distinct branches of humanity, shaped by their environments. If one day people dwell in free-floating space habitats with artificial gravity, or even in microgravity for generations, they too might adapt uniquely. In this way, the human story could diverge across space, each population molded by its new home. We're far from that, but the seeds of it are visible in how quickly and subtly our bodies respond to even short stays in orbit. We've already begun evolving culturally, and perhaps one day biologically, to be a spacefaring species. The transformations, puffy faces, weaker legs, stronger appreciation for Earth's gravity, broadened perspective, are part of the pioneering price and reward. They underscore that when we finally send humans on years-long voyages to Mars or establish outposts on the Moon, we will be changing ourselves as much as the environment. Space does not just permit life, it challenges life to transform, and in doing so reveals what is essential and what can adapt. Having set tentative footsteps beyond Earth, our gaze naturally turns to horizons ahead. What destinations lie within reach for the next chapters of our journey? Mars, for one, has beckoned for generations. So have the Moon's beckoning plains for a sustained return, the resource-rich asteroids, and beyond them, the giant planet's intriguing moons, and then, ultimately, the stars themselves as the far frontier. The Moon is likely our next close step. After the first era of human moon landings, humanity took a hiatus, but plans are well underway to go back, not just to visit, but to stay. The vision is a permanent lunar base, perhaps at the moon's south pole, where ice lurks in shadowed craters. That ice could be harvested into water, oxygen, and even rocket fuel by splitting water into hydrogen and oxygen. A lunar base could serve as a research station, like an Antarctic outpost, studying the moon's geology, testing technologies for living off Earth, and serving as a proving ground for longer missions. It's humbling and thrilling to imagine future explorers waking up in a habitat on the moon, stepping outside in suits to see the Earthrise on the horizon of an airless sky, tending greenhouse plants under low gravity, mining regolith for materials, and practicing the art of survival on another world. Mars, the red planet, has captured human imagination for centuries. Though farther away, a journey of months, it offers a place that in some ways is more hospitable than the moon. Mars has an atmosphere, thin as it is, day-night cycles similar to Earth's, and essential elements like carbon, nitrogen, and water, as ice, accessible on its surface. The draw of Mars is profound. It's a planet that once had liquid water flowing on its surface, and perhaps was warm enough for life billions of years ago. If life ever arose there, traces might remain in the soil or rock. And if life did not arise, Mars presents a canvas for possible future habitation, a second home for humanity, though one requiring domes and life support to sustain us. Plans for Mars involve sending humans in the not-too-distant future. Maybe the first crew will step onto Martian soil within a couple of decades. They would endure a 6 to 9 month voyage through interplanetary space, likely spend a year or more on the surface, exploring and doing science, and then undertake another long journey home. The challenges are immense: exposure to radiation during the trip, the psychological toll of isolation and distance. Earth would shrink to a tiny, star-like point in the Martian sky at times, with radio signals taking 10 or 20 minutes one way, and the need to be largely self-sufficient so far from help. Landing on Mars is no small feat either. Its thin atmosphere is tricky, not enough to slow a spacecraft as easily as Earth's air does, but enough that you can't ignore it. Yet, robotic missions have shown it's doable, and designs for habitats, rovers, and ascent vehicles are on the drawing board. We can imagine that historic day. A human being sets foot on Mars for the first time. The gravity is only a little more than a third of Earth's, so their steps have an odd bouncing lightness. The sky overhead is a butterscotch orange hue, and the sun, though bright, appears smaller and cooler than on Earth. As they look around, they see an empty expanse of reddish desert extending to distant dusty hills. There is no sound except the ones they make. Mars's thin air carries almost nothing. At twilight, perhaps, they will see Earth as a pale blue star winking into view, a tiny beacon of all they left behind. In that moment, all of human history to date will be looking back at them across the gulf of space, and all of humanity's future beyond Earth will be opening in front of them on that silent Martian plain. If and when humans establish a foothold on Mars, it will represent a turning point, becoming a multi-planet species. The first settlers might live in habitats shielded by Martian soil, grow plants in controlled environments, and systematically explore for resources like subsurface ice or useful minerals. Over time, they might build more permanent bases, maybe even attempt small-scale terraforming experiments, though making Mars truly Earth-like would be a project for centuries or millennia, if it's feasible at all. The first child born on Mars would mark a new branch of humanity no longer tied entirely to Earth's cradle. Beyond Mars, the solar system offers other tantalizing targets. There's talk of sending humans to visit asteroids, small worlds which could be rich in metals and water. A mission to an asteroid would test deep space travel techniques and give experience in low-gravity operations. Asteroids could one day be mined to build structures in space, or to obtain water for sustaining space settlements and fueling rockets. Water, being heavy, is expensive to lift from Earth, but abundant in some asteroids. The idea of using asteroids as stepping stones or resource depots takes shape. One can imagine a network of fuel stations in space derived from asteroid mining, enabling easier travel to Mars and beyond. The moons of the outer planets also intrigue scientists and the public. Jupiter's moon Europa hides a deep ocean beneath its icy crust. Saturn's moon Enceladus jets geysers of water into space from another subsurface sea. Saturn's Titan has a thick atmosphere and lakes of liquid methane. These are far, harsh places for humans to reach with current technology, but they tantalize because of their uniqueness and their potential for harboring life, at least microbial life in those hidden oceans under ice. In the far future, one could imagine research outposts orbiting these moons, or even submersible probes someday swimming in Europa's ocean. For now, these remain domains for our robots. Human footsteps on those worlds are likely a very distant dream. Humanity's more immediate future in space likely involves building up infrastructure, space habitats and fuel depots, better propulsion systems, and learning how to utilize what's already out there. In situ resource utilization, as engineers call it. People dream of giant rotating space stations that produce artificial gravity, where hundreds or thousands could live and work, maybe as way stations between Earth and Moon or Earth and Mars. Concepts like massive rotating cylindrical settlements have been proposed to house communities in space in the more distant future, using materials mined from the Moon or asteroids. Such colonies could even have agriculture, parks, and small towns inside spinning megastructures, creating a shirt-sleeve environment in the void. While purely conceptual now, they fire the imagination of what a truly spacefaring civilization might eventually create. If we project progress forward, one can imagine a time where the solar system is alive with human activity. Perhaps lunar mining outposts supply raw materials and fuel, while rotating habitats at Lagrange, points between Earth and Moon, house thousands in simulated gravity. Mars could host bustling research towns beneath pressurized domes, with children who have never felt Earth's heavy gravity running freely under a salmon-colored sky. In the asteroid belt, factories might forge spacecraft from spaceborne metals, and on the moons of Jupiter, laboratories could drill into subsurface oceans in search of alien microbes. Spacecraft, both crewed and robotic, would shuttle along established routes, and way stations would speckle the darkness, making deep space feel a bit more traversable. It would be a future where our species is not bound to one world, where Earthling becomes Solarian, a citizen of many worlds. This may sound like science fiction, but it's essentially an extrapolation of what our ingenuity could achieve with time, resources, and the continued drive to explore. The seeds are already visible in our current ventures. And then there are the stars. Interstellar travel, going to another star system, is the grandest of dreams, currently well beyond our engineering. The nearest star, apart from the Sun, is over 4 light-years away. With chemical rockets, it would take tens of thousands of years to reach even that closest neighboring star. That hasn't stopped us from dreaming and even planning precursors. One idea is to use powerful ground-based lasers to push many tiny, ultralight sails to a significant fraction of the speed of light. These star chips could reach the Alpha Centauri system in a few decades and send back pictures of any planets. It's a wild idea under study, representing an early attempt to make interstellar reach possible, at least for probes within a human lifetime. For crewed flight, proposals often verge on science fiction, generation ships where entire societies live and die during a voyage lasting centuries or millennia, suspended animation or stasis for travelers, or engines that harness exotic physics, like antimatter or fusion drives, to drastically cut travel time. While the stars are distant, they remain a locus of aspiration. Every advance we make, nuclear propulsion, closed-loop life support, faster communications, brings what was once impossible slightly closer to the realm of the possible. One day far ahead, humans, or our AI descendants or engineered successors, might actually embark on journeys to other star systems, perhaps finding new homes around alien suns. The timeline for such ambition is hard to predict, centuries, millennia, longer, but it underscores a fundamental aspect of our relationship with space. We are never content to stay. There is always a next horizon. From cave dwellers venturing over mountains, to seafarers crossing oceans, to astronauts leaving Earth orbit, the unknown beckons. In dreaming of moon bases, Martian colonies, asteroid mining, and interstellar crossings, we carry forward the same wonder that made us look up at the Milky Way in ancient times and weave tales about it. Our modern rockets and probes are our ships of legend. The destinations may no longer be mythic heavens, but real physical worlds. Yet the emotional pull is similar. Space offers an endless frontier that challenges us to grow, technologically, intellectually, ethically. Will we become caretakers of multiple worlds? Will we spread life to barren planets, making gardens in the desert of space? Or will we simply learn to appreciate and safeguard the precious oasis of Earth by seeing how rare and daunting other places are? The dreams of the future run on both practical and romantic rails. Practically, establishing a human presence beyond Earth increases our species' chances of survival if disaster befell our home world, and it opens up vast resources for use. Romantically, it fulfills something deep in our psyche, an urge to explore, to know the unknown, to step beyond boundaries. Space is the ultimate embodiment of those boundaries, and crossing each one is a giant leap for our collective being. As we plan these leaps, from returning to the moon to eventually reaching another star, we do so with a mix of scientific rigor and childlike wonder. It is perhaps the greatest adventure we can undertake, to leave our cradle and see what lies outside, and in doing so, to discover not just new worlds, but new facets of ourselves. Reaching other stars with conventional technology is daunting. But human curiosity doesn't stop at what seems unreachable. It imagines ways to transcend barriers. This is where speculation and cutting-edge physics meet. What if we could cheat the cosmic speed limit or take shortcuts through space-time? What if our universe is not the only one? These questions, once purely philosophical, are now topics of serious scientific hypothesis, though still highly theoretical. They ignite our imagination about what space could allow, under laws of physics we are only beginning to glimpse. One such speculative concept is the wormhole. Envision space-time as a stretchable fabric. A wormhole would be like a tunnel or shortcut through that fabric, connecting two distant points via a shorter hidden path, almost like a secret door in a mansion that lets you jump from one wing to another without walking the long corridor. If such wormholes exist and could be stabilized, a traveler might enter one end and emerge far away, perhaps in another galaxy or even another universe. Wormholes arise as possible solutions in the equations of general relativity under certain exotic conditions. But to hold a wormhole open so it doesn't pinch off, calculations suggest you'd need negative energy or pressure, something not present in ordinary matter in bulk. We've observed hints of negative energy in quantum effects, like the Casimir effect between close plates, but nothing that can be amassed to engineer a traversable wormhole. So for now, wormholes remain hypothetical. They tantalize with the idea of instantaneous cosmic journeys and even time travel, since a wormhole might allow moving backward in time under some setups. But they also warn us with paradoxes. Nature, as far as we know, isn't in the habit of handing out free passes through time and space. There may be fundamental constraints that keep wormholes from being useful or stable. Still, they populate science fiction and theoretical physics papers alike, perhaps the ultimate wild card in the cosmic deck. Another audacious idea is the warp drive, the notion of bending space around a vessel so that it effectively moves faster than light relative to distant observers, without locally breaking the light speed limit. The most famous concept was put forward in the 1990s, a solution of Einstein's field equations suggesting that if you could form a warp bubble contracting space ahead of a ship and expanding it behind. The ship could ride this bubble and cover distances faster than light would in normal space, all while the ship itself sits in a local pocket where it doesn't technically break the speed of light. It's like surfing a wave of space-time. The catch? Early calculations indicated you'd need absurd amounts of negative energy or mass, that troublesome requirement again, and energy on scales beyond anything conceivable. Initial analyses said more mass energy than exists in the observable universe. Later refinements lowered the energy requirements significantly, but it's still far beyond anything we can envision with known physics. Additionally, generating and controlling a warp bubble raises deep questions. How would one form it? How to steer it? What happens to any matter in the bubble's path? Some worry a warp bubble's sudden formation or collapse could blast the destination with high-energy radiation. These remain firmly theoretical issues. In essence, wormholes and warp drives are solutions in our equations that haven't been ruled out by math, but whether nature permits them is unknown. We have no experimental evidence that such things exist or can be made, but the fact they aren't outright forbidden by current understanding keeps the door ajar for future breakthroughs. They are reminders that space-time itself is an active player, and maybe, just maybe, can be engineered in ways we currently find fantastical. Now consider an even grander idea, that our space isn't the only space. The concept of a multiverse posits that what we call the universe, the totality of space and time we see, might be just one bubble in a frothy sea of universes, each with its own space, time, perhaps its own physical laws or constants. This arises from various considerations in cosmology and quantum physics. For instance, eternal inflation theory suggests that while our region of space underwent a rapid expansion, inflation, and then slowed to form the cosmos we know, other regions of space might still be inflating, budding off bubble universes endlessly. In that picture, new universes are constantly born, like a cosmic foam, each disconnected from the others, space beyond space. Another multiverse idea comes from quantum physics. The many worlds interpretation of quantum mechanics imagines that every quantum event that could have multiple outcomes does, in some sense, realize all outcomes, each in a separate branch of reality. These branch universes would be parallel to ours, diverging whenever outcomes differ. In those universes, different histories unfold. If that interpretation is taken literally, then reality might constantly be branching into a multitude of timelines. But those are not reachable spaces, just alternate possibilities given form. They don't exist in our physical space, but in a sort of abstract space of configurations. Yet another notion. Perhaps other three-dimensional spaces exist embedded in higher dimensional space. String theory, for example, has suggested a cosmos with 10 or 11 dimensions, where our familiar 3D space could be a brain floating in a higher dimensional bulk. Other brains might float alongside ours, normally invisible and untouchable, but may be able to interact via gravity or other subtle forces. If that were true, another entire universe could be millimeters away in a fourth spatial dimension, and we'd never know, unless some leakage, like unexplained gravitational effects, hinted at it. So far, we have no definitive evidence for this either, but it remains a provocative possibility. If any multiverse idea is true, it expands our notion of space dramatically. Space would no longer be an all-encompassing singular stage, but one stage among countless others. It might answer deep questions like why our universe has the properties it does. Maybe countless universes have varied properties, and we happen to live in one that supports life. It would also raise new questions. Could we ever detect or interact with these other universes? Most frameworks suggest no, at least not easily. Other universes would be causally separated or on different branes of reality. These speculative frontiers, wormholes, warp drives, multiverses, lie at the fringes of science, where it blurs into philosophy and imaginative conjecture. They remind us that space, as weird and rich as we found it to be, might be even weirder and richer than we can currently prove. Some of these ideas might turn out to be impossible, others irrelevant, or maybe one will surprise us and become part of mainstream physics in the future. For now, they serve as a mental playground, pushing us to ponder what the true limits of travel and existence are. If one day a wormhole mouth is held open in a lab or a tiny warp bubble detected, it would revolutionize our approach to space, turning the impossible into the achievable. If evidence of a multiverse emerged, say, a peculiar pattern in the cosmic microwave background hinting at another universe bumping into ours in the distant past, it would transform our understanding of what space really means on the grandest scale. So we allow ourselves to dream beyond the known laws, not irrationally, but as an exercise in curiosity. How far can the concept of space be stretched? Can we step outside our universe or bring distant corners within reach? These questions keep scientists theorizing at chalkboards late into the night and storytellers spinning tales of cosmic voyages. They highlight an essential truth: space is not static. It is full of potential surprises. Until we try or observe, we cannot be entirely sure what is and isn't possible. Thus, the speculative frontiers remain an open chapter, waiting for the day when perhaps advanced beings, maybe our descendants, treat wormholes or hyperspace jumps as casually as we treat airplane flights. And even then, beyond them would lie more unknown, for infinity has a way of always extending beyond the farthest frontier. After traversing the tangible and the theoretical, we arrive at a contemplative vista. We have seen space as both absence and fullness, both distance and connection. We've imagined diving through wormholes and living on Mars. But underlying all these discussions is a more fundamental question. What is our relationship to space? We often speak of space as a backdrop, a stage on which matter, stars, planets, people, performs the play of life. But one might ask, is space merely the stage, or is it part of the cast? And are we simply in space, or are we made of it and by it? At first glance, space seems like an empty container, and we like the players moving through it. Yet consider that without space, we have no stage at all, no arena for existence. Space defines how we separate objects and moments. The distances shape the dance of gravity. The silence shapes the significance of sound when it occurs. The emptiness shapes the structures that form. In this sense, space is an active participant in the cosmic drama, not a passive backdrop. It sculpts the narrative. The expansion of space drives galaxies apart. The curvature of space choreographs the motion of planets. The quantum fluctuations in space seeded galaxies themselves. Now think of ourselves. We tend to imagine we live in space. On Earth, under an atmosphere, yes, but Earth itself is in space, orbiting the Sun, which orbits the galaxy, and so on. We draw a mental line at the edge of our atmosphere and say, space begins there. But in truth, space is already here. It's between you and this page or screen. It's inside your body, vast gaps between atoms. You are as much in space on Earth's surface as a fish is in water at the bottom of the ocean, just under different conditions. The fish might not realize it lives in water. We often forget we live in space. We are also of space in a profound way. The atoms that compose us were forged across space. Hydrogen from the Big Bang's expanding fireball, carbon and oxygen cooked in the hearts of ancient stars across the galaxy, iron fused in the violent explosion of a supernova light years away. Those atoms traveled through interstellar space, perhaps as part of drifting gas clouds or microscopic dust grains, eventually coalescing in the cloud that formed our solar system. They became part of Earth, part of the air, part of the water and food chain, and now part of us. In that lineage, we are literally made of stardust and cosmic debris. Our flesh and bones are cosmic matter arranged in the pattern we recognize as human. So can we truly say we are separate from space? Or are we a condensation of space's contents, temporarily gathered and self-aware? If space is the stage, we are pieces of the stage that have learned to dance and sing about itself. And if space is the play itself, the unfolding story of the universe, then we are characters in that play, but also made of the very substance of the stage. The dichotomy breaks down. Space is not just an external void we venture into. It is a part of us, and we are part of it. We emerged from the universe, not into the universe. When a baby is born, we don't ask, into what room is it born, as if the room defines it. Likewise, humanity was born from cosmic processes, out of space and matter's interplay. We did not enter the universe at some moment, we grew out of it, like an apple grows from a tree. The apple might contemplate the orchard and realize it is of the same essence as the tree that bore it. This perspective shift, seeing ourselves as an expression of the cosmos rather than mere inhabitants in it, has deep implications. It can instill a sense of belonging rather than alienation. When we say, the universe is vast and we are insignificant, that is one viewpoint highlighting scale. But another viewpoint is, we are the universe, in that part that has become conscious and is marveling at itself. In that sense, our significance is cosmic. We are how the cosmos knows and admires its own grandeur. Both views have truth. It's a matter of context. We are tiny in size compared to galaxies, but size isn't the only measure of significance. We are rare and miraculous in our complexity, a testament to what space and matter can do given enough time and the right conditions. The stage versus play question also touches on whether space itself has agency or is purely passive. While space doesn't think, it certainly reacts and evolves. It carries waves. It expands. It can even produce particle pairs spontaneously. In a way, the story of the universe is as much the story of space evolving as it is of matter moving. One could poetically say, space is the main character, with matter and energy as its attributes or children that give it shape and color. These musings border on the philosophical and poetic, but they arise naturally when confronting the reality of what space is. We see ourselves historically as separate, humans versus environment, life on Earth versus space beyond. But zoom out, and that division fades. The Earth is a tiny island in a sea of space, but the sea permeates the island too. Ultimately, there is one continuous reality, the universe. In it, matter, including us, and space are deeply interwoven. Distinctions are practical for analysis. We distinguish object and background. But at the fundamental level, space and content define each other. One might ask, if a tree falls in a forest and no one hears, is there sound? In space terms, if space were completely empty of matter and observers, would it still exist or have meaning? Perhaps yes, as a potential stage. Perhaps no, because nothing would be there to measure it. But the actual universe never presents pure space devoid of everything. It's always space-time coupled with fields at least. And now, it has conscious beings within it who can reflect on it. As we reflect, we realize that as we travel into space, we are not leaving home behind. We are bringing one part of space, ourselves and our vessels, into another part of space. When we left Earth for the moon, it was a reunion of sorts, two pieces of the same cosmic puzzle meeting. The humans made of Earth materials stepping onto lunar soil. Both were once part of the same primordial nebula. Space exploration is thus space self-interacting in new ways. So, are we in space or of it? The answer can only be both. We exist within space, moving through it. And every particle of us is a piece of the cosmos, born from it, and ultimately to return to it when our atoms disperse. Is space the stage or the play? Space is the stage, the set, and part of the cast. It sets the scene, influences the plot via physical laws, and even occasionally takes center focus, as when we contemplate a black hole or the expanding universe itself. The play is the unfolding of everything, matter, life, thought, upon that stage, and space is present in every scene. This unity of space and actors invites a sense of reverence. Not reverence in a religious sense necessarily, but a humble appreciation that we are integral to a vast cosmos. As much as we talk about conquering space or exploring space, we are really exploring a larger reality that we are intrinsically part of. We extend ourselves when we extend into space. We learn about ourselves when we study space, because the same rules that govern the stars govern the atoms in our bodies. Space is not out there, it's around us and within us. This realization erases a bit of existential loneliness. We are home wherever we go in the universe, because we never truly leave the universe. We are made of it. Amid all these grand scales and bold ventures, there is something quietly astonishing, that we, lumps of organized matter, can contemplate all of this. Consciousness, the fact that the universe has, in us, and perhaps elsewhere, developed eyes to see and minds to wonder, is itself a cosmic phenomenon. How does awareness fit into the story of space? Think about what a thought is in physical terms. A thought is a pattern of electrical impulses and chemical signals moving through a network of neurons in a brain. Those neurons are cells made of molecules, those molecules of atoms. Those atoms were forged in stars. The brain is a piece of organized cosmos, fed by oxygen and nutrients, ultimately products of Earth's biosphere and the sun's energy. So every idea you have is essentially space, matter in space, rearranging itself in a complex dance that somehow yields subjective experience. In a poetic sense, when you look up at the night sky and feel awe, that is the universe marveling at itself. Starlight that traveled for eons triggers electrochemical sparks in a brain that evolved on a planet, producing an emotion of awe and understanding. The photons from a galaxy 2 million light-years away end their journey on your retina. Signals shoot through your brain and you recognize the galaxy and feel wonder. The cosmos communicates with itself through us in that moment. Throughout history, humans have sensed something spiritual or transcendent in stargazing, the feeling of being connected to something far larger. Today we can articulate it in scientific terms, but the feeling remains profound. We are connected. We are made of the same stuff we observe. Our thoughts arise from physical processes that obey the same laws that govern planetary orbits and galactic rotations. It's all a unified tapestry of cause and effect, from quarks to quasars, with consciousness woven in as one of the newest, most complex threads. Is consciousness common in the universe or exceedingly rare? We do not know. As far as we're aware, on this little planet, matter became alive and, in our species, became aware of itself after billions of years of cosmic evolution. Perhaps on some exoplanet under an alien sun, other beings gaze at their night sky and wonder as well. Or maybe intelligent life is so improbable that we are solitary minds in a vast, mindless expanse. Either reality is awe-inspiring. Either the universe is teeming with many centers of consciousness, many eyes and minds, or we are a unique jewel, the universe's single point of self-reflection. In either case, the emergence of mind from matter is one of the most remarkable aspects of this cosmos. We scan the skies for hints, radio signals that might betray intelligent life, chemical signatures in exoplanet atmospheres that could indicate biology. So far, the universe has been quietly eloquent. We have found thousands of planets around other stars, some potentially hospitable, but no clear sign of life or mind beyond Earth. Still, the search is young. With each passing year, our instruments improve, and with each new world discovered, our sense of the possible expands. Maybe tomorrow we'll detect a whisper from across the galaxy, or maybe, against the odds, our spark of awareness is uniquely solitary. Either outcome deepens our appreciation of existence. Either we share the universe with other curious beings, or we are rare pearls, tasked all the more with cherishing and spreading life. Consider the extreme, deep intergalactic space, utterly dark and quiet. And then consider a human mind, perhaps an astronaut on a long voyage between planets, carrying within them memories, songs, hopes, and the capacity for imagination. That mind can recall the sound of ocean waves or the face of a loved one, even while physically surrounded by vacuum. In the void of space, within the confines of a helmet, the richness of subjective experience continues. Thoughts, dreams, and emotions, intangible and invisible, somehow accompany the traveler. They have no weight, no volume, yet they exist as surely as the oxygen tank or the spacecraft walls. This juxtaposition of the inner universe of consciousness and the outer universe of space is a great mystery. How does awareness arise from non-aware components? How did the cosmos go from a blazing plasma to quiet clouds, to living cells, to thinking beings? We understand pieces of the process, physics to chemistry, to biology, to neurobiology. But the subjective feel, what it is like to be alive and aware, still puzzles philosophers and scientists. It's as if the cosmos has secret attributes, mind, qualia, that only emerge at high levels of complexity. Some have poetically suggested that perhaps consciousness pervades all matter in some tiny degree, a philosophy called panpsychism, or that the universe and consciousness are deeply linked, as some interpretations of quantum mechanics muse when noting that observation seems to affect reality. These ideas remain speculative. The mainstream view is that our minds are emergent properties of matter, but what a wondrous emergence! In contemplating space, we often focus on what's out there, but there's also space within. Our minds create a mental space, a canvas of imagination where we can simulate travels and picture galaxies. That inner space is just as remarkable. It has no physical volume, yet it can contain infinite scenarios. We can imagine flying to the edge of the universe, or conjure up entirely fictional worlds. This inner space is the playground of thought, and it interacts with outer space through our actions and creations. Every rocket that ever launched was first conceived in the inner space of someone's mind. Thus, the story of space is not just about stars and vacuum, but also about awareness arising and reflecting on it all. It's a narrative thread that connects the coldness of cosmic voids with the warmth of human experience. Thought floats on matter, like a flame on a candle, ephemeral yet tied to the physical. Awareness shines in the dark, like a brief spark in the vast night, yet illuminating so much. Knowing this, when we speak of exploring space, we are also exploring the potential of consciousness. Each discovery out there expands the universe in here, our understanding. The boundary of what we consider ourselves and the cosmos gets blurred. With each insight, the cosmos becomes part of us in knowledge, and we become part of the cosmos in presence. The age-old questions, what are we? Why are we here? Are we alone? Are as much questions about space as about us, because to answer them, we must look outward and inward simultaneously. It's humbling and ennobling to realize that mind is a late-born child of space, a spark that the deep darkness brought forth. We, as conscious beings, are the universe's way of contemplating itself, a thought beautifully expressed by many thinkers in various forms. Our brains, tiny as they are compared to galaxies, contain patterns that mirror the cosmos in understanding. In the profound darkness, aware minds are like lanterns, small, but casting light in the intellectual sense, revealing the structure and secrets of all that is. Now, as our journey through thought nears its end, let us reflect on where we stand. Think of what ground we've covered: space as emptiness and fullness, the birth of space and time in a fiery genesis, the paradox of the quantum vacuum in its nothingness. the bending of space-time giving rise to gravity, the way light's travel reveals the past, the unimaginable gaps from atoms to galaxies, the grand cosmic web, the acceleration of expansion by dark energy, the silent scaffolding of dark matter, the enigmas of black holes, the edge of our visible universe, humanity's first forays into the void, the transformations of life in microgravity, the dreams of new worlds, the wild ideas of wormholes and multiverses, and finally the thread of consciousness stitching it all together. We began by looking at space as darkness and distance, the emptiness between things, and ended by seeing it as something that also resides within us, the very fabric of our existence. Space is our origin. We can trace our lineage not just through human history or life's evolution on Earth, but further back through the birth of the sun, the formation of the galaxy, to the creation of elements in stars, to the Big Bang's initial conditions. Every step of that path took place in space, and because of space. The vast molecular cloud that collapsed to form our solar system was a product of space's expansion and the debris of older stars. The Earth formed from cosmic matter orbiting in space. Life sparked in Earth's oceans under a sky of stars. We are, in a very real chain of events, children of the cosmos. We were born from stardust, shaped by the laws of nature in an expanding space. Thus, space is our ancestral home, the delivery room in which Earth and life were born. Space is our element. Just as a fish lives in water, we live in space. It may seem counterintuitive because we feel solid ground under our feet and breathe air, but those exist within the larger framework of space. Remove space, and there's nowhere for ground or air to be. In a sense, space is the medium that holds us, as the atmosphere is the medium a bird flies through. And as we've seen, even within our bodies and atoms, space is the dominant component. We are more void than substance by volume. This isn't to say we are empty, rather that emptiness is an integral part of what we are. Space gives structure to the dance of particles that is us. We truly are beings of space. Space is our home. Our minds often conceive home as a small place, a house, a town, a planet. But in the grand scheme, our true home is the universe itself. There is nowhere else. Every attempt at escape still lands us in some other part of the cosmos. When future explorers set foot on Mars or sail between stars, they will still be within the universe, just changing rooms in the grand mansion. Recognizing the universe as home fosters a kind of cosmic belonging. The stars are not alien or distant in an existential sense. They are kin, made of the same matter energy and subject to the same space-time fabric. The nebulae that dot the galaxy are nurseries that will birth new stars and perhaps new life. They carry on the homemaking that began with the Big Bang. In this view, to harm our home planet is to harm one oasis, but the greater home of space will endure. Conversely, to cherish our planet is to honor the gift that the universe's processes have given us. Our ultimate loyalty, one might poetically suggest, could be to the cosmos and life as a whole. Standing outside on a clear night, you might feel small under the wheeling stars. And yes, one human is a tiny speck in a vast galaxy. But that galaxy is within you too, in your atoms, in your comprehension. We end where we began, the quiet darkness, the twinkling lights. But now, perhaps, we sense that the darkness is not empty. It's full of context and connection. The distance is not disconnection. It's the very thing that allows everything to be. The silence is not lifeless. It set the stage for our music. In the end, space is not just a void we inhabit. It's the foundation of every story we tell, including the story of our own lives. Decades ago, a spacecraft departing the solar system turned its camera back and captured our Earth as a mere pale blue dot suspended in a sunbeam against the blackness of space. That image spoke volumes. It showed our home as a fragile, singular pixel in the cosmic darkness. It emphasized viscerally that all we hold dear, every life, every mountain, every civilization, exists on that tiny dot. Such perspectives have become part of our collective understanding. They remind us that to explore space is also to gain wisdom about cherishing one another and our planet. We have come to see that the boundaries we imagine between nations or between ourselves and the cosmos are in many ways illusions. So look up. Feel the slight tug of gravity anchoring you to your planet. Feel the air that was brewed in distant stars fill your lungs, and realize that you belong here, in this universe, in this space. We all do. The stars, the galaxies, the people, the particles, we're threads in one inconceivably vast tapestry. Space is the fabric on which we're drawn, but also the thread from which we're woven. In that unity, there is a profound peace. We do not live in a cold, meaningless void. We live in a cosmos of endless possibility that has given rise to galaxies and, on at least one tiny world, to love and curiosity. Space made this possible, and space will carry us forward. It's as though a voice older than memory has been speaking to us through the silence, telling a tale our ancestors began to whisper under ancient skies, a tale we always intuitively knew, but are only now beginning to understand through science. We are children of space, knit from its fabric and warmed by its fires. In its vastness, we find our challenges and our solace. The silent night sky is not the end of the story, but the beginning, an invitation to explore, to learn, to feel. And as long as we have wonder, the darkness will never be empty. For the emptiness is full of stories, and we are part of its telling. In that spirit of unity and wonder, we continue our journey, part of the universe, seeking to know itself amid the endless ocean of stars. In the cosmic silence, our questions and dreams are the voice that rings out. As long as we listen and strive, the conversation between humanity and the universe will go on, growing richer with each generation. What wonders await us in the vast reaches still unexplored? Who knows? The only way to find out is to keep journeying with open minds and open hearts into that infinite frontier. The story of space is far from over, and we are its authors as well as its audience. In the beginning, there was silence, a silence deeper than night, softer than a held breath. Nothing moved, for nothing yet existed that could move. No stars, no galaxies, not even the whisper of a breeze in the dark. In this primordial stillness, before light and time and form, there was only a pregnant pause, an infinite calm awaiting a spark. And then, in that void, something happened. A flash, a burst of unimaginable brightness, and the silence was broken. The universe was born in an eruption of light and energy, a silent explosion that rang with no sound, yet carried the promise of everything to come. From that moment, space unfurled like a new scroll, stretching, expanding, filling with the first hot glow of creation. Still, there was no ear to hear, no eye to see. All was energy and plasma and the slow birth of matter. Yet, as the cosmos burgeoned outward, the silence remained underneath the cosmic symphony, like a bass note holding all melodies, the backdrop of the vast expanding space. Eons passed in wordless majesty. Stars kindled across the darkness, clustered into galaxies, swirled into patterns by gravity's gentle but inexorable hand. Great structures formed, filaments of galaxies and voids larger than anything we can truly imagine. In all of this grandeur, in all the furnace roar of stars and the collisions of galaxies, a profound silence still reigned. It was not an empty silence, but a pregnant one, the silence of a universe in the making, as yet without anyone to witness it. Nebulae blossomed like cosmic flowers, stars lived and died, forging heavy elements in their hearts and scattering them into the void. Planets coalesced around distant suns. Perhaps on countless worlds, oceans pooled and gentle winds blew under alien skies. But for ages, no voice broke the silence, no mind yet asked a question. On one tiny planet, Orbiting an ordinary star in an ordinary galaxy, something miraculous stirred. Life. In warm, shallow seas, simple microbes began to live, multiply, and evolve. The silent universe had given rise to tiny living things that could sense and respond. They knew nothing of the larger cosmos, only the immediate instinct to survive. But life grew more complex and daring. It crept onto land, took on myriad forms in oceans and forests. And in time, on that little blue world, consciousness sparked. Creatures emerged who could wonder. They looked up at the night sky with curious eyes. They felt small under the canopy of stars, yet compelled to reach out in thought. From their lips and hearts came the first question: what is all this? Where did it come from, and why? Thus, in a corner of the universe, the great silence birthed a question. It was perhaps the first time the cosmos had been asked to reflect on itself through the very beings made of its dust. In those early questions, uttered around flickering campfires or silently pondered under the wheeling stars, the universe itself found a voice. Through us, the cosmos began to speak and to ask. A strange paradox. Out of the universe's stillness grew minds that would not be still, that hungered to know. The night sky's grandeur made early humans feel both awe and mystery. They saw patterns in the stars and spun stories, sensing perhaps that the darkness was not empty, that there was something vast and eternal out there, beckoning. Who placed the stars in the sky? What lies beyond that glittering curtain? Is the universe around us all there is, or just a piece of something far greater? These questions, simple and profound, were the beginning of our journey. And they have no end. As though space itself were whispering to us, we felt an urge to explore, to seek the limits of what we can see. We learned to build tools, first telescopes of glass and metal, later great observatories, to extend our vision deeper into the silence. With each improvement of our cosmic eyes, the known universe grew. What once was a dome of twinkling lights became an ocean of stars, then countless galaxies, and then structures beyond galaxies. We discovered that the stars are not scattered randomly. They are gathered in immense cities of stars, the galaxies, each containing billions or trillions of suns. Our own Milky Way is one such city, a flat disk of light arcing across the sky. And beyond it, we found others. Andromeda, the whirlpool shapes of spirals, the blob-like ellipticals, the tiny dwarfs swarming around bigger ones. We realized the universe is composed of these galaxies scattered through space like handfuls of luminous sand tossed into the dark. Through patient observation, we determined the scale of our cosmic neighborhood. Light, that fastest of messengers, takes years to cross the gulfs between stars and millions of years to travel from one galaxy to another. We began to grasp that the lights in the sky were incredibly distant. The deepest images, taken with sensitive instruments, staring for days into what seemed like an empty patch of sky, revealed a staggering sight. Hundreds of galaxies in just a pinprick of darkness. It was like finding a shimmering city on what looked like a blank horizon. Everywhere we point our telescopes, if we look long enough, galaxies appear. The observable universe, the portion we can in principle see, contains at least 2 trillion galaxies, each with billions of stars. These numbers defy imagination. Even as we say them, do we truly understand? Each galaxy, an island of stars, perhaps with planets and wonders of its own, multiplied by trillions. The scale humbles us. We sit on a small planet orbiting one star among those countless, and we realize we are tiny. Our world is a mere grain of sand on an endless beach. As our knowledge expanded, so did our questions. We found that the universe has an edge, but not an edge in space like a wall or boundary we could touch. Rather, a limit in time and light. We call it the observable universe, the region from which light has had time to reach us since the universe began. There may be more beyond, much more, but it lies forever outside our view, hidden behind a horizon of light. Why can't we see beyond? Because the universe has a finite age, about 13.8 billion years since the Big Bang fireball ignited existence as we know it. Light from very distant regions simply hasn't had time to travel to us yet. Imagine being in a vast wilderness at night with a lantern. You see trees around you in the lantern's glow. Beyond a certain distance, the forest is dark, not because it ends there, but because the light hasn't reached those faraway trees. Our cosmic horizon is like that, a sphere of light around us, 46 billion light-years in radius, beyond which the universe fades into an unknowable darkness. And yes, that horizon's radius is larger than 13.8 billion light-years because space itself has been stretching all the while, carrying distant galaxies further out. We peer out to the edge of what we can see, and it appears like a foggy wall, not a solid barrier, but a limit of clarity. That fog is actually the afterglow of the Big Bang, the cosmic microwave background radiation, faint heat left from the time the universe was a hot, dense plasma. It's as far back as light can show us, a view of the universe when it was only about 380,000 years old, beyond which it was opaque. So here we stand, creatures of stardust and curiosity, staring at the cosmic horizon. We strain to see if beyond that faded glow of the primordial fireball there might be more, perhaps endless galaxies receding into eternity. We suspect the universe doesn't simply end past what we can see. The evidence whispers that space likely continues far beyond our observational reach. The patterns of temperature in that cosmic afterglow are almost too smooth, too uniform, as if our observable patch is just a tiny piece of a much larger whole. If the cosmos ended just past our horizon, space would likely curve visibly or wrap strangely. Instead, all measurements indicate space is very nearly flat on the largest scales, with no detectable curvature as far as we can tell. This implies either the universe is infinite, stretching on without end, or so vast and curved so gently that we have not yet seen the bend. Most cosmologists lean toward the idea that it might be effectively infinite, or at least extremely large beyond comprehension. If that's true, our observable universe could be a mere grain in an infinite desert of universes. Think about that for a moment. Beyond the furthest galaxy we can see, there may be countless more galaxies, and beyond them more without edge. If space truly goes on forever, then somewhere out there, far beyond the reach of any telescope, other beings might gaze at their night sky and see a patch of galaxies that includes our Milky Way as just a faint smudge. Or perhaps they are so distant that even our whole observable universe is just a tiny part of their view. In an infinite cosmos, possibilities become certainties. Somewhere, the arrangements of matter must repeat. It boggles the mind, but in an infinite expanse, there could be another region so far away that it is identical to our own in content. Another patch of space with galaxies arranged just like ours. Another Earth with someone just like you, reading these very words. This isn't science fiction. It's a logical implication of infinity, although it's practically unobservable and forever beyond our interaction. The idea is dizzying and a bit unsettling, an infinity of other realities just out of reach. Yet it reminds us how limited our perspective is. We sit in our tiny bubble of space-time and see 93 billion light-years across. But that might be like looking through a keyhole and thinking that's the entire world. We simply don't know how far the grand stage extends. The true extent of the universe could be infinite, or the universe might eventually loop back on itself in a grand cosmic curve, like the surface of a sphere, but in 3 dimensions. If space is curved into a finite shape without a boundary, it's conceivable, though unlikely in light of current data, that if we traveled in one direction far enough, billions of light years, we might someday end up back where we started, coming up behind ourselves like a traveler circumnavigating a globe. Some scientists have even speculated about exotic shapes for space. One proposal imagined the universe's shape as a kind of dodecahedron, a 12-faced polyhedron, stitched together in a way that the cosmic microwave background might show repeating patterns. For a time, there were hints in the data, faint patterns that could suggest we were seeing the same regions of space in multiple directions, as if light had wrapped around the universe. But so far, these hints have not solidified into proof. The simplest explanation, flat and potentially infinite, remains most plausible. Yet the shape of the universe, its global geometry and topology, remains one of those great unanswered questions. Is the cosmos infinite or finite? Does it have an overall curvature or a unique topology beyond our horizon? We live suspended between possibilities, unable to step outside the universe to see it from the outside. Standing on the shores of the cosmic ocean, we realize that not only is there a limit to what we can see, but that the universe is astonishingly old and dynamic. The cosmos we observe is not eternal and unchanging. It has a history. The galaxies are flying apart, space itself stretching and carrying them away from each other. When we first discovered in the early 20th century that distant galaxies all seemed to be rushing away, it was as if the universe were breathing out, expanding. Rewinding this expansion with our calculations, we found it all converges back to that fiery beginning, the Big Bang. That was a revelation. Our universe had a birth in time. There was a moment, however brief, when all that we see and all that we cannot see was concentrated in an inconceivably hot, dense state. Before that, we do not know if before even exists in a meaningful sense, since time itself might have begun with the Big Bang. This origin story is derived from solid evidence: the expanding space, the cosmic background radiation, the mix of light elements. Yet it leaves us with profound mysteries. What ignited the Big Bang? What, if anything, came prior? Was it truly the beginning of everything, or just the beginning of our cycle of reality? We humans, naturally curious, push against the curtain of the unknown. We have conjectured many ideas for what set the stage for our universe. Some propose that our Big Bang might have been one of countless others. Perhaps the universe goes through cycles of birth, death, and rebirth, a bouncing cosmos that contracts and then explodes anew, over and over. Others imagine our universe budding off from a parent multiverse, a foam of bubble universes endlessly forming like bubbles in boiling water, each bubble a universe with possibly different properties. In such scenarios, the Big Bang was not the absolute beginning, but simply our bubble's local genesis. Still others invoke the idea of quantum fluctuations. Maybe nothingness is inherently unstable, and a tiny fluctuation could tunnel into creating an entire universe. Our cosmos could have sprung from a quantum event out of a vacuum of some higher reality. These ideas venture far beyond the realm of testable science, at least for now, but they arise naturally from our attempt to answer the question of origins. The truth is, we don't know what caused the Big Bang, or if that concept even makes sense in the absence of time. The very word cause assumes time already exists to allow an effect to follow, and if time began at the Big Bang, asking what came before might be as meaningless as asking what's north of the North Pole. Not knowing, however, does not stop the questions, it fertilizes them. Each mystery begets more wonder. We gaze at the observable universe, at that limit of perception, and wonder, if there are things forever beyond our sight, how can we ever know them? Perhaps we cannot, but we can infer hints. For example, our observable universe seems remarkably uniform in temperature in all directions. Even regions that are so far apart, light couldn't travel between them in the age of the universe to even out the heat. How did opposite ends of the sky agree on the same temperature without being in contact? To solve this puzzle, scientists proposed a radical idea: inflation. In the infant moments of the cosmos, a fraction of a second after the Big Bang, space itself might have blown up exponentially fast. An extreme expansion that took a tiny, uniform region and stretched it so vast that all we see now originated from that same patch. This would explain why distant parts of the sky have the same ancient heat signature. They were once close before inflation shoved them far apart. Inflation neatly accounts for some observed properties, suggesting our whole observable universe was once an infinitesimal speck. But inflation, if true, also dramatically broadens our perspective. That initial tiny region after inflation became huge, far larger than what we now observe. And inflation might not have been a one-time event that ended cleanly everywhere. Many inflation theories predict that inflation might be eternal, still occurring in far-flung regions, continually spawning new bubbles of space that themselves go on to expand and cool, becoming universes in their own right. In this picture, our universe is one bubble among a potentially infinite multiverse. Each bubble might have different physical conditions, different types of particles, even different dimensions or laws. We have no way, at present, to confirm the existence of other universes. They would be beyond our horizon, causally disconnected from us. Yet the theory that predicts them arose from trying to explain things we can see, lending some credence to the concept. The multiverse idea tickles the imagination. It suggests a reality far larger or more varied than anything we can directly detect. If true, the great silence beyond our cosmic horizon might be filled with other universes we will never know, a sobering and exhilarating possibility. Some of those universes could be barren, lifeless expanses where stars never formed. Others might be strange, with physics so alien that atoms as we know them can't exist, and perhaps some might be kindred to our own, with galaxies and stars, maybe even life. Of course, these speculations might forever remain philosophical musings. Without evidence, they remain in the realm of the unknown. But it is astonishing that human minds, products of a single universe, can even conceive of realities beyond it. Our imaginations press outward to the ultimate limits of existence, refusing to accept an end to the story. The cosmos, through us, is pondering what lies beyond itself. Yet, even as we dream of multiverses and infinite space, we must contend with enigmas right here in the observable universe, mysteries woven into the fabric of the cosmos we see. In the late 20th century, as our instruments grew more precise, we encountered one of the most profound. We realized that we understand only a tiny fraction of the cosmic contents. All the stars, planets, galaxies, everything that shines, or that we can detect with any form of electromagnetic radiation, amount to a mere 4 to 5% of the total mass energy of the universe. The rest, the vast majority, is invisible to our eyes and instruments, yet its presence can be felt through gravity. This realization dawned gradually, starting with the way galaxies rotate. We expected, based on the gravity of visible stars and gas, that stars at a galaxy's outskirts would orbit more slowly, just as planets farther from the sun move more slowly, weakened by distance. But to our surprise, we observed that stars in the outer reaches of galaxies were moving just as fast as those closer in. It was as though some extra gravitational force was present, something we couldn't see, holding the outer stars in orbit and preventing them from flinging away. The same unseen influence showed itself in other ways. Clusters of galaxies, huge collections where hundreds of galaxies orbit a common center, were behaving as if they had far more mass than what our telescopes could account for. Light from distant galaxies was found to be distorted and magnified by massive invisible clouds, like a giant lens made of something transparent. All these clues pointed to one conclusion. An unknown form of matter permeates the universe, outweighing normal matter by a factor of about 5. We called it dark matter, not because it's dark like soot, but because it neither emits nor absorbs light. It's utterly invisible, detectable only by its gravity. What is dark matter? We still don't know. It could be some new kind of elementary particle that doesn't interact with light or normal atomic matter except through gravity. Perhaps faint, ghostly particles left over from the Big Bang that pass through Earth and through our bodies by the billions every second without a trace. Experiments deep underground and in particle accelerators are attempting to catch a glimpse of a dark matter particle. But so far, they've only placed limits on what it could be. It's humbling. We have this elegant theory of fundamental particles and forces, the standard model, that describes atoms and light and so much else, and yet it doesn't include a particle that can account for dark matter. So either there is physics beyond our current theories, a new particle, a supersymmetric partner, a hidden sector of forces, or, just possibly, our understanding of gravity on large scales might be incomplete, meaning what we attribute to unseen matter could be a subtle shift in how gravity works over vast distances. Most evidence favors actual dark matter substance, because the patterns are hard to explain with modifications of gravity alone. Dark matter is like a shadow universe overlain on the one we see. It formed a cosmic scaffolding in the early universe. Imagine an invisible web, filaments and knots of dark matter, and normal matter fell into its gravitational wells. This process seeded the formation of galaxies and clusters along the dark matter web. In a sense, the luminous structures we observe, galaxies, stars, planets, and us, are arranged on the template that dark matter provided. Yet we cannot directly behold this scaffolding. We map it indirectly by observing how it bends light, gravitational lensing, and how it influences the motions of galaxies. What an irony that most of the universe's mass is invisible to us. We are like fish swimming in water, yet not seeing the water, only sensing its currents. The dark matter neither shines nor bumps into atoms in a way we can easily measure. It whispers to us only through gravity, the subtlest of clues. We have given it a name. We hunt for it with detectors in deep mines and in the Large Hadron Collider. And perhaps one day we'll finally hear its voice. Until then, it remains a tantalizing mystery, a vast, unknown sea in which the islands of stars float. As if that weren't enough, an even stranger revelation awaited us. At the turn of the 21st century, astronomers painstakingly measuring the expansion rate of the universe made a shocking discovery. They expected to find that the expansion, slowed by gravity over time, was either coasting gently or perhaps starting to decelerate more strongly if the universe had a lot of matter. Instead, they found that the expansion isn't slowing at all, it's speeding up. The galaxies are not just rushing apart, they're accelerating away from each other, like a driver who, instead of coasting uphill, suddenly floors the gas pedal. This was the last thing anyone expected. Whatever could be causing this acceleration was not something we could see. It wasn't normal mass, which would attract, not repel. We named this mysterious phenomenon dark energy, a term that is a placeholder for our ignorance. Dark energy seems to make up about 70% of the total energy content of the cosmos, dwarfing even dark matter, which is 25%, leaving ordinary matter as a cosmic afterthought. What is dark energy? That question cuts to the core of our understanding of physics. One possibility is that dark energy is a property of space itself. In the equations of general relativity, Einstein's theory of gravity that describes how matter and energy tell space-time how to curve, there is a term, the cosmological constant, which Einstein once introduced and later retracted, thinking it unnecessary. This term corresponds to an inherent energy of empty space, an energy that doesn't dilute as space expands. If space has an innate energy, it would act like a sort of pressure or anti-gravity that pushes things apart. And indeed, this cosmological constant idea fits the observations fairly well, a constant energy density in space that started dominating the universe's dynamics a few billion years ago, causing expansion to accelerate. But why would such a constant exist, and why of that particular magnitude? When physicists try to calculate how much energy empty space should have, based on quantum theory, where even vacuum teems with virtual particles popping in and out, the theoretical value comes out enormously larger, a ghastly mismatch with what we observe. It's one of the worst disagreements between theory and observation ever encountered, signifying we deeply misunderstand something. So perhaps dark energy isn't a simple constant. Maybe it evolves, a dynamic field that changes over time, a concept dubbed quintessence after the fifth element of the ancients. Quintessence would be a new substance or field filling space, one that can vary from place to place or era to era, and whose properties we have yet to determine. Another wild possibility: perhaps our understanding of gravity needs revision at the very largest scales. Maybe, like Newton's laws were superseded by Einstein's relativity might itself be a limiting case of a deeper theory that yields an accelerating cosmos without invoking a mysterious energy. For now, dark energy remains an enigma. It's as if we're children who notice that a top is spinning faster on the tabletop than it should, yet we can't see the hand twisting it. The universe's acceleration is a clue that our cosmic story has a twist, literally a speeding up, and we're in the dark, pun intended, about why. What we do know is that given this acceleration, the future is quite bleak for our view of the cosmos. If dark energy continues to push the expansion, distant galaxies will rush away faster and faster. Far in the future, beyond tens or hundreds of billions of years, other galaxies might recede so far and so fast that their light can no longer reach us. An observer in that far future might see an empty universe, just their own galaxy and nothing else, unaware that other galaxies ever existed. The thought that the rich cosmos we observe is a temporary gift of this epoch is poignant. We happen to live when the universe is young enough that galaxies are still in view. The accelerating expansion means the vast majority of galaxies are slipping beyond reach, like ships sailing over a horizon from which they'll never return. But why this is happening? Why now, and what exactly dark energy is? Those answers elude us. The silence regarding dark energy is profound. We can measure its effects with exquisite precision, yet the cause of those effects remains a whisper from the void. From the grandest scales of the expanding universe, let us turn inward to one of the most fearsome and fascinating objects nature allows: black holes. These are regions where matter has been crushed into such density that the fabric of space-time itself has curled in on itself, creating a pit from which nothing, not even light, can escape. A black hole forms, for example, when a massive star reaches the end of its life. The star's core collapses under its own weight, compressing beyond even atomic structure, beyond anything we can properly imagine, until it becomes an infinitely dense point, a singularity, wrapped in a spherical cloak of gravity. The boundary of that cloak is called the event horizon. Once you cross that threshold, there is no return. The concept of an event horizon is chilling and intriguing, a one-way membrane in the universe. Outside it, space and time behave normally. Inside, all paths inexorably lead down to the central singularity. It's a point of no return, a cosmic trap door. Black holes challenge our understanding of physics at a fundamental level. According to general relativity, the singularity at the center has infinite density and zero volume, a place where the known laws of physics break down completely. This signals that our theories are incomplete. Infinities in equations often mean we're pushing the theory beyond its domain of validity. We need a theory of quantum gravity, combining quantum mechanics with gravity, to fully describe what happens at those extreme densities. But we don't yet have that theory. So inside the black hole, hidden from our view by the horizon, nature keeps her deepest secret. It's as if the universe has places it refuses to show us, where it hides the answers to the final exam of physics. What would it be like to fall into a black hole? Imagine approaching a black hole in a spaceship. From a safe distance, it might actually be quite invisible unless it's feeding on surrounding matter, which can glow brilliantly as it heats up falling in. If it's a solitary black hole, you'd see stars behind it, warped into rings or arcs by its intense gravity, gravitational lensing. As you got closer, the pull on your ship would increase. If the black hole is of stellar mass, the gradient of gravity between your nose and tail is so steep it would stretch you out in a process morbidly named spaghettification. You'd be torn apart before you even reached the horizon. But if it's a supermassive black hole, like the ones at galactic centers, millions of times the mass of the Sun, The tidal forces at the horizon might be mild, since the gravity, while strong, changes more gradually across your body. In that case, you could actually cross the event horizon without immediate destruction, and perhaps without even noticing crossing it, since nothing particularly physical marks that boundary aside from the point of no return property. Once inside, however, all paths lead to the center. Your engines, no matter how powerful, cannot reverse course. Time and space trade roles in a sense. Just as you cannot stop moving forward in time, now you cannot stop moving toward the singularity. According to classical relativity, within a short time you reach the central singularity and are crushed. Your mass adds to the black hole, your identity lost. But physical intuition rebels. Is information truly destroyed in a black hole? Quantum theory says information about a system's state cannot be lost. At least, that's a principle of quantum mechanics as we understand it. If a black hole simply eats things and then evaporates, we suspect black holes slowly evaporate via Hawking radiation, a faint glow due to quantum effects at the horizon. What happens to the information that fell in? Hawking radiation, as originally conceived, carries no information. It's like heat radiating from a warm object, basically random. If a black hole completely evaporates away, does the information of everything it consumed just vanish from existence? That possibility horrified physicists, as it seemed to violate a sacred tenet of physics: information conservation. This is the famous black hole information paradox. Some think the information is encoded in subtle correlations in the Hawking radiation, so that in principle, if you capture all the radiation, you could reconstruct what fell in. Others have proposed exotic solutions. Perhaps the singularity isn't the ultimate end. Maybe it somehow connects to a new region of space-time, a budding universe or a white hole, theoretical time-reversed black hole that spits matter out. Some suggest that what we call singularity might be a mischaracterization, and quantum gravity, when understood, will show no infinite crunch, but something like a bounce or a portal. Yet others imagine that black holes might have firewalls at the horizon, blistering zones of quantum energy that destroy information before it even reaches the singularity, thus preserving quantum rules, but at the cost of violating Einstein's predictions of a smooth passage through the horizon. We just don't know the answer yet. Astonishingly, what was once theoretical musing, we have now seen. In recent years, humanity managed to capture an image, via radio telescopes arrayed across Earth, of a black hole's shadow, essentially the silhouette of the event horizon against the backdrop of hot plasma around it. The first such image, of the supermassive black hole in the galaxy M87, showed a fuzzy donut of light, just as predicted by general relativity. We have also measured gravitational waves, ripples in space-time itself, from black holes colliding, hearing the literal ringing of space-time as they merge. These observations confirm that black holes are real, not just mathematical quirks. They exist in the universe by the dozens, likely by the millions. Our own Milky Way harbors a giant black hole at its core, over 4 million times the mass of the Sun. Stars orbit this invisible monster like comets around a phantom sun. And nearly every galaxy likely has one, with masses from millions to billions of solar masses, shaping the evolution of their host galaxies in ways we're still investigating. So black holes stand as both a triumph of understanding, we predicted them, then observed them, and a frontier of mystery. Their insides remain terra incognita. They force the question of how the very large, gravity and space-time, and the very small, quantum particles, mesh together. To truly know what a singularity is, or what happens at that boundary of physics, we will need a unified theory that marries quantum mechanics with general relativity. It's often said that at a black hole's center, the equations of general relativity yield infinity, meaning the theory throws up its hands. It's as if at that point, the universe is saying, "Here, your current understanding halts. A new understanding must begin." In the same vein, consider the nature of time itself, another profound mystery at the intersection of physics and philosophy. Time is something we all experience intimately, yet when we scrutinize it, it becomes elusive. We feel time flow. Every moment, we sense the now moving inexorably to the next now. We remember a fixed past. We anticipate an unknown future, and we seem trapped in this ever-moving present. But what is time? Physics treats time as a dimension much like space. In relativity, time and space are intertwined as space-time. Just as we can move north-south or east-west, we also move forward in time. But why do we only move in one direction in time, whereas in space, we can turn around? Why is yesterday set in stone and tomorrow so contingent? This one-wayness is called the arrow of time, and it appears most strongly when we consider entropy, the measure of disorder. The second law of thermodynamics says entropy in an isolated system tends to increase. Eggs scramble, but they don't spontaneously unscramble. Smoke disperses from a fire, but never gathers itself back into logs. In short, things tend to move from order to disorder, from concentrated energy to spread out energy. This provides a kind of arrow from a past of lower entropy to a future of higher entropy. Our memories and records are traces of lower entropy states. Perhaps the reason we remember the past and not the future is simply that the past is embedded in those ordered traces, like photographs, fossils, neurons in our brain, whereas the future hasn't left any traces yet. In this view, the arrow of time is a brute fact about initial conditions. The universe started in a very low entropy, highly ordered state. The Big Bang, despite being hot and dense, was actually very uniform, which is a kind of order. As the universe evolves, entropy increases. Stars burn fuel and produce heat, matter clumps and then energy dissipates, etc., thus giving time a direction. But this explanation, while broadly accepted, just pushes the mystery back one step. Why was the entropy low to begin with? Why was the early universe so orderly, laying the groundwork for an arrow of time that would later allow life and memory? We don't know. It might be a fortunate accident, or it might hint at deeper cosmological structure. For instance, in some multiverse scenarios, maybe new universes always start fresh with low entropy as they pinch off, and we naturally find ourselves in one of those. Another puzzle. At the microscopic level, the fundamental laws of physics, ignoring a subtle detail with certain particle decays, are mostly time-symmetric. They don't care if time runs forward or backward. If you filmed two particles scattering off each other and ran the movie backwards, you'd see a perfectly valid physical process. Yet at the human scale, time's asymmetry is obvious. How do those reconcile? The prevailing view is that the asymmetry isn't in the underlying laws, but in the boundary conditions. Again, that low entropy past. Thus, the flow of time might be emergent, not fundamental. Some scientists even propose that time as we perceive it, a flowing river, is an illusion, a byproduct of our consciousness stringing together events, whereas in reality, all moments might coexist in a block universe. In that block universe picture, the past, present, and future are all equally real, just different coordinates in space-time. And it's only our particular perspective, like a spotlight moving along the timeline, that gives a sense of flow. This interpretation is mind-bending because it means now is not a universal truth, but a subjective one linked to each observer. Relativity already showed that simultaneity is relative. Two events that are simultaneous for you might not be for me if we're moving differently. So in a deep sense, the notion of a global present is tricky. Is time perhaps an emergent phenomenon from something deeper, like entanglement or quantum states? Some cutting-edge ideas suggest time might arise from quantum entanglement patterns, or that our universe's time dimension could have sprung forth from a timeless quantum reality when certain conditions were met. These remain speculative, but they remind us that something as fundamental as time is still not fully understood. Time is at once the most familiar thing and the greatest mystery. We live in time. We cannot step outside it to examine it objectively. That's akin to asking a fish to describe water. It's so ubiquitous that it becomes elusive. We mark time's passage with clocks and calendars, but what we're really measuring is change relative to other change. A second is defined in physics by a certain number of oscillations of a cesium atom's radiation, for example. So time is tied to processes. If nothing changed, would time have meaning? In the vast stillness before the universe, if such a state can even be contemplated, what was time? Or did time begin when change began? The silence of the cosmos extends into the subatomic world as well, where our everyday intuitions falter. Peering into the quantum realm, we found uncertainty and paradox. The building blocks of reality, electrons, photons, and other quantum particles, do not behave like little billiard balls following neat paths. Instead, they exist as fuzzy clouds of possibility, described by a wave function that tells us only the probability of finding them in a particular state. It's as if, at a fundamental level, nature doesn't decide on an outcome until something forces its hand, namely, an observation or interaction that makes the potential become specific. This is encapsulated in Heisenberg's uncertainty principle. One cannot precisely know certain pairs of properties, like position and momentum, at the same time. If you pinpoint a particle's location, its momentum becomes uncertain. If you know its momentum exactly, its location smears out. Nature, it seems, imposes a fundamental limit on how much we can know, or perhaps on how much is decided, even in principle. This isn't a limit of technology, but of principle. It's as though the universe, at fine scales, refuses to give a straight answer, offering instead a spread of possibilities. Consider the famous double-slit experiment. When we send electrons or photons one by one through two narrow slits to a screen, an interference pattern emerges, as if each electron were a wave that went through both slits and interfered with itself. Yet, when we put detectors to see which slit the electron actually went through, the interference disappears. The electron acts like a particle that went through one slit or the other, not both. It's as if the electron exists in a ghostly blend of possibilities, both paths, until we look, and then it chooses one path, retroactively making itself a particle that had gone that way all along. This kind of behavior defies our classical logic, and the universe stays mum on how or why it happens. Various interpretations of quantum mechanics try to make sense of it. Some say the wave function collapse is just fundamental and random. Others propose that each possible outcome actually branches off into a separate reality. The many worlds interpretation, where the electron went through left slit in one branch and right slit in another, and these two branches do not interfere once decoherence, entanglement with environment, has happened. Many worlds offers a wild vision. Every quantum event spawns a new universe, so there is an ever-branching multiverse of possibilities. If true, then at this very moment, innumerable versions of reality are splitting off for every quantum choice. In some, you took a breath a second later than in others. In some, a butterfly flapped its wings, whereas in others it stayed still, and those small differences proliferate. This would be a multiverse of a different kind, not separated by vast distances, but coexisting on top of each other in a higher dimensional quantum space, splitting at each interaction. It's a solution to making quantum mechanics purely deterministic. No randomness, just every outcome happens in some branch. But it means that reality is unimaginably more complex than we perceive. Yet from within one branch, we can never communicate with the others. So how could we ever tell if this is true? The cosmos yields phenomena that invite such bizarre explanations, and then remains silent, leaving us to debate and wonder. Another perplexing quantum phenomenon is entanglement, what Einstein famously called spooky action at a distance. When two particles are entangled, they share a single quantum state. If you separate them across the galaxy and then measure one, instantly the other is affected, or rather, instantly you discover that the outcome on one side is perfectly correlated with the outcome on the other side, as if they were connected. For example, two photons can be entangled in polarization, such that if one is measured to be vertically polarized, the other will always be found horizontally polarized, say the opposite, no matter the distance. It's not that one sends a signal to the other at measurement. As far as we can tell, nothing travels between them, and indeed, if you try to use this for communication, it fails. You can't actually send a message this way. Instead, it's as if the two particles are a single entity described by one combined wave function, and when you collapse it by measuring one, you simultaneously collapse the whole system. This is deeply counterintuitive. It implies the universe has non-local qualities. Parts of the universe far apart can be intimately linked in ways that transcend ordinary space and time relationships. Experiments have confirmed entanglement again and again. It's real. We even have technologies exploiting it, quantum cryptography, for instance. But why the universe allows this deep connectedness, how it fits with our concept of locality, and what it means about the underlying reality, remains mysterious. Some thinkers speculate that perhaps space and time themselves are not fundamental, and entanglement hints at a more basic fabric of reality from which space emerges. Picture that what's fundamental is information or relationships, and what we perceive as space is just a way of organizing those relationships for our macro understanding. In such a view, two entangled particles might be adjacent in the deeper reality, even though in our three-dimensional space they are far apart. Thus their coordination is instantaneous because distance is irrelevant in the underlying layer. This is speculative, but it's an attempt to make sense of what nature is quietly demonstrating to us without explanation. The silence of the quantum world, the lack of an intuitive story from nature about what's really happening, has haunted physicists and philosophers for a century. Richard Feynman once said, "I think I can safely say that nobody understands quantum mechanics." It's a humbling admission that even our best theory, confirmed by experiment to astonishing precision, is something we can use, mathematically, but not fully comprehend in plain language. Is the electron a particle or a wave? The only honest answer, it's something quantum, which has aspects of both, and depending on how we interact with it, it will manifest one aspect or another. It's as if reality at base is described not by the solid objects of our sensory experience, but by ghostly probability clouds and interconnections that defy straightforward description. We've developed a comfortable routine with quantum mechanics. Shut up and calculate, some say. Yet the human spirit itches to truly know, to have a picture, a narrative, something that feels resolved. And so far, the cosmos offers none. Perhaps one day a deeper theory, like a successful quantum gravity theory or a theory of everything, will unify these pictures and give us a new paradigm that makes quantum weirdness feel as natural as sunrise. Until then, we live with a fundamental not knowing at the heart of physics. Our journey through the unknown wouldn't be complete without reflecting on the mysteries that hit closest to home. We've looked outward to the edge of the universe and inward to subatomic realms. But what about life? What about consciousness? These are aspects of the cosmos too. After all, we are part of the universe, made of the same particles and subject to the same laws. In the cosmic perspective, life is a recent phenomenon, blossoming on at least one small world. But is it unique to Earth or common as starlight? This is one of humanity's oldest questions. Are we alone? The Earth teems with life in astonishing variety and tenacity. We find life flourishing in boiling hot vents at the ocean floor, in acidic lakes, in the frozen Antarctic permafrost, and high in the atmosphere. Life, once it gains a foothold, is hardy and adaptive. This gives us hope that life could exist beyond Earth, in niches we once thought too extreme. Perhaps in the subsurface oceans of icy moons like Europa, or Enceladus, or in the cloud decks of Venus, or on planets orbiting distant stars. We have now discovered thousands of exoplanets, planets around other suns. Some of these are in the so-called habitable zone, where temperatures might allow liquid water. A few are near Earth size and could be rocky. The sheer number of planets in our galaxy is staggering, likely on the order of 100 billion, roughly one per star on average, and many stars have multiple planets. With billions of galaxies, the number of planets in the observable universe might be more than all the grains of sand on all Earth's beaches. If even a small fraction of those planets are habitable, the number of living worlds could be enormous. And yet, we have not heard a peep. The universe, as far as our searches have detected, is quiet about life beyond Earth. No radio signals from alien civilizations beam through the sky, despite our listening via SETI for decades. No unmistakable technological signatures or visits, despite UFO lore. There's no confirmed evidence of extraterrestrial craft. We see no obvious ruins on Mars or elsewhere in the solar system. This great silence is puzzling. It's termed the Fermi paradox. Given the vastness of the cosmos, and presumably many opportunities for life, why have we not encountered anyone or anything? Where is everybody? Enrico Fermi famously asked. There are many possible answers, none confirmed. Maybe life is common, but intelligent life is exceedingly rare. Perhaps simple microbes abound on many worlds, in the oceans under ice crusts of moons, or beneath the soils of exoplanets. But the evolution of complex multicellular life, and then technological intelligence, is an extremely improbable chain of events. After all, for most of Earth's history, billions of years, life remained single-celled. Only in the last 500 million years did complex organisms proliferate, and only in the last few million did a species arise with intelligence capable of radio telescopes and rockets. Perhaps in many biospheres that step never occurs. Life stays microbial or animalistic, never building cities or machines. Or maybe civilizations do emerge on many planets, but they tend to have short lifespans. They might self-destruct via warfare or environmental collapse. Or perhaps they inevitably transition to some other state, like a virtual reality existence, and lose interest in communicating with the stars. It could even be that a galaxy teems with life and intelligence, but it's largely quiet and inward-looking, and the distances are so vast that communication is difficult. Signals might be rare, or we might not recognize them. Perhaps advanced beings use communication methods we haven't discovered, or maybe they abide by a cosmic etiquette, a prime directive, of not interfering with emerging civilizations like ours. It's also possible we are alone, or at least incredibly rare. Maybe life itself is a freak occurrence, needing such a special convergence of circumstances that Earth might be one of only a handful of places in the whole galaxy or beyond where it happened. Some scientists have suggested that certain unlikely events, like the origin of life from chemistry, or the jump from single cells to complex organisms, or the development of intelligence, might be low-probability flukes. If so, the universe could be mostly sterile, with us as a precious exception, or one of very few. That thought is both exhilarating, we're special, and terrifying, so fragile in the cosmic darkness. If we are rare or alone, it puts a huge responsibility on us, to survive, to cherish life, to perhaps spread it. We are searching avidly for answers. Our robots crawl on Mars, drilling into rocks to find traces of past microbes. Our probes have sampled the plumes of Enceladus, shooting water from its subsurface ocean into space, and found organic molecules, tantalizing, though not proof of biology. We're designing missions to Europa and other worlds. And from Earth, or Earth orbit, we are beginning to peek at exoplanet atmospheres. We've detected atmospheres on a few distant planets, and soon next-generation telescopes will try to find signatures of life. For example, an atmosphere rich in oxygen, which on Earth is maintained by life, or weird combinations of gases that scream metabolism at work. It's a challenging task. Exoplanets are tiny and drowned out by their bright stars. But the endeavor is underway. Perhaps in the coming decades or centuries, we'll get our first hint that biology is not unique to Earth. Imagine the day we detect, say, methane and oxygen and water vapor on an Earth-sized planet around a distant star, a combination hard to sustain without life. We will not hear aliens say hello, but we might finally know that the cosmic loneliness is an illusion, that life has filled other ponds in the great rain of creation. Until then, we have only questions and the emptiness between the stars. We've sent out our own signals, radio waves that have leaked from our transmitters for a century, spreading out as a faint bubble. 100 light years in radius, and we've deliberately beamed a few focused messages or carried plaques and golden records on spacecraft like the Voyagers. Those artifacts drift now in the interstellar void, likely to wander for millions of years. Perhaps one day, far future, some alien hand, or appendage or machine, will find our little bottles in the cosmic ocean and know that we existed. But for now, the only confirmed life in the universe that we know of is here, on this pale blue dot. That is a sobering truth. It means every living thing we have ever known, every experience of love, joy, struggle, discovery, all of it, has occurred in a thin film of life on one planet's surface. Life is a delicate chemical flame fighting entropy, and Earth is the oasis that nurtures it in our solar system. This knowledge urges us to protect our world, for if life is rare, losing Earth's biosphere would be an unspeakable tragedy. And if life is common, well, then we have friends yet to meet, and we should keep our planet thriving so that one day we might join a galactic community. Either way, the quest to know if we are alone goes on, intertwined with our own future. And then there is consciousness, the most immediate reality to each of us. For what could be more certain than our own awareness? Yet perhaps the hardest phenomenon to explain in scientific terms. Somehow, in the 13.8 billion year journey from the Big Bang's fire to now, the universe has developed the ability to contemplate itself. Hydrogen atoms coalesced into stars. Stars forged heavier elements. Those elements made planets. On one planet, chemistry begat life. Life grew brains, and now those brains contain minds that experience, question, and create. It sounds like a fairy tale, inert matter becoming sentient, yet it happened. In us, and likely in other creatures too, to varying degrees. Surely many animals are conscious in their own ways, though we humans possess a self-reflective awareness and intellect that sets us somewhat apart. How does mere matter give rise to the feeling of being? How does a collection of neurons, exchanging electrochemical signals, produce the redness of a rose, the taste of chocolate, the pang of sadness, the sense of self? This is often called the hard problem of consciousness, because explaining how the brain processes information, responds to stimuli, or controls the body, the easy problems. Those are difficult, but we can see how to approach them scientifically. But explaining why those processes should be accompanied by an inner subjective experience, why there is something it is like to be you from the inside, that's a different matter. We might map every neuron in your brain and track every spike and chemical, and still be left wondering at what point those physical events create a conscious experience. If a computer simulated your brain perfectly, would that simulation be conscious? Or is there something more than computation needed? Science, by design, deals with third-person observations, measurements of things from the outside. Consciousness is inherently first-person. It's the one thing you can't directly observe about me, nor I about you. I can tell you I feel pain or joy, and you can correlate it with brain activity or behavior, but the feeling itself is private. This gap between objective and subjective has led to philosophical standoffs for centuries. Mind-body problem, dualism versus physicalism, etc. The prevalent scientific view is that consciousness arises from brain activity, that the brain is the generator, or at least the transmitter, of the mind. If so, then consciousness should be explainable in terms of neurons and their interactions, but we haven't cracked how. There are intriguing leads. Certain brain processes correlate strongly with conscious states. For instance, synchronized oscillations in certain frequencies, or specific circuit loops in the cortex and thalamus. The Integrated Information Theory, IIT, suggests that consciousness corresponds to the amount of integrated information a system possesses, a measure noted as FEF. Under IIT, even a simple system might have a tiny bit of consciousness if it has a feedback structure that integrates information. So even a thermostat might have a minuscule glimmer of experience, which is a panpsychist kind of implication. Another theory, Global Workspace Theory, GWT, posits that consciousness is like a global blackboard in the brain, where information gets broadcast to many subsystems. What we experience consciously is the stuff that made it into this global workspace. These theories provide models and prediction, but none yet explains why the global workspace feels like something, or why integrated information should result in an inner life. Some thinkers have ventured that consciousness might be a fundamental property of the universe, like mass or charge, an idea known as panpsychism, the notion that perhaps all matter has some degree of consciousness, and complex systems like brains just amplify or collect it into the vivid awareness we know. This is not a mainstream scientific view, but it arises from the difficulty of explaining consciousness purely as emerging from non-conscious parts. If electrons and neurons are totally devoid of experience, how do a trillion of them together produce experience? Panpsychism answers, maybe electrons, and all particles, have extremely rudimentary proto-consciousness, some intrinsic aspect that is mental, and when arranged in complex ways, these form higher consciousness. It's a wild idea, harking back to ancient philosophies that saw spirit in all things. Whether true or not, it underlines how desperate the attempt to solve consciousness has become, that even such ideas get consideration. Alternatively, maybe consciousness is an emergent phenomenon that will eventually be explained in terms of information processing, but we just haven't found the right concepts yet. After all, concepts like temperature and pressure were once mysterious. How does the jostling of atoms create the feeling of warmth? But kinetic theory explained them. Perhaps one day we'll likewise demystify conscious experience, showing how certain patterns of computation just are the subjective feeling from the inside, similar to how a certain frequency of air vibrations just is the subjective experience of a musical note to an ear and brain. Some neuroscientists suggest that if you had a matrix of interconnected neurons or artificial units replicating the brain's structure, an inner life might spontaneously light up. But verifying that will be tricky, again, because we can't directly measure the consciousness, only infer it from behavior or reported experiences. For now, consciousness stands as an open question that straddles science, philosophy, and even spirituality. The cosmos has produced self-aware beings. We know this because we are them. But we don't understand the spark that lights up our thoughts. We don't know at what point in evolution consciousness arose. Do fish feel? Do insects? What about single-celled organisms responding to stimuli? Is there a faint glimmer of something it is like to be an amoeba? Does consciousness require a brain, or could an alien form of life, like a network of fungi or even a sufficiently complex machine, be conscious? Could the universe itself be conscious in some way, as some mystics and even a few scientists muse? Not in a simplistic anthropomorphic way, but in a sense that there is a level of awareness associated with the cosmos as a whole, or with fundamental fields. These questions drift at the edges of empiricism. They may not all be answerable, at least not by traditional experiments, yet they matter to us, because consciousness is the lens through which we experience everything else. Without it, we aren't even there to ask the questions. Let us step back now and look at the tapestry of what we know and what we don't know. The cosmos began, as far as we can tell, in silence and mystery, and that mystery remains at every level we probe. We have learned so much: the age of the universe, the recipe of elements, the existence of cells and DNA, the laws of gravity and electromagnetism, the reality of quantum fields, the genealogy of stars and galaxies, the expansion of space, the evolution of life. Our knowledge has blossomed, an impressive collective achievement for a species of former cave dwellers. And yet, what we don't know overshadows the patch of light we've kindled. The volume of ignorance is an ocean around our island of understanding. It humbles us, but it also excites and motivates us. Each generation has pushed further into that ocean. We often find that answering one question opens several new ones. We learned how stars shine, but that led to questions about stellar evolution and supernova. We discovered other galaxies, but that raised questions about dark matter to explain their motions. We uncovered the expanding universe, which posed the question of what the fate of expansion is and introduced dark energy. We deciphered the code of life, DNA, but then faced the complexity of how genes lead to consciousness. It's like climbing a mountain. Each time you reach a summit, you find a higher peak beyond. Far from being disheartening, this is invigorating. It means the adventure continues, perhaps forever. Consider the nature of space itself. At first glance, space seems like nothing, an empty void, the backdrop for matter. But we've come to see space as something with structure and activity. Einstein's relativity showed that space and time can stretch, bend, and ripple. Gravity, in that theory, isn't a force emanating through space. It is the shape of space and time itself, curved by mass and energy. When you put a heavy object like the sun in space, it dimples the space-time fabric around it, and the Earth orbiting the sun is like a ball rolling around a dent, following curves in space-time. This was a radical shift. Space is not just an inert stage, it's a dynamic actor. Then quantum physics adds another layer. Even a perfect vacuum, completely devoid of particles, isn't truly empty. It seethes with ephemeral phenomena, quantum foam, as some call it. Particles and antiparticles can briefly appear and annihilate. Fields fluctuate constantly at microscopic scales. There is a constant jitter in the vacuum, so much so that the vacuum, paradoxically, contains immense energy if summed, though our inability to tap or see most of that energy is another puzzle. These vacuum fluctuations have real effects. They cause tiny, measurable forces, the Casimir effect, where two close plates have a slight attraction due to altered vacuum modes between them, and contribute to phenomena like the Lamb shift in atomic physics. So the nothingness of space is actually a roiling, boiling brew of potential, the foundation upon which everything rests. Space itself might undergo phase transitions. Some cosmologists speculate that in the very early universe, space was in a different state, with different symmetry between forces, and as it cooled, it crystallized into the form we know, possibly releasing energy that drove inflation. The vacuum today might hide exotic fields, like the Higgs field, which pervades space and gives particles mass, discovered experimentally in 2012. A tangible example that space contains fields with constant values. Dark energy could be the energy of space's vacuum. If space has energy, then a volume of vacuum isn't truly nothing. It's more like a latent something. We're reminded of a line from a poet or sage that silence is not empty, it's full of answers. Similarly, space is not empty. It's full of the answers to questions we've yet to formulate. Yet for all that, when you stand outside on a clear night and look up, space feels like an immense, silent void between the stars. That serene emptiness cradles all of creation. It separates and connects everything. Every breath you take, the molecules were at one time scattered in space before the Earth formed. And after you exhale, given enough time, they may escape Earth and wander the galaxy. Space allows that movement. Space, by its vastness, also ensures that objects can exist without immediately colliding with one another. It grants stability to solar systems and galaxies by giving them room. But is space infinite? Does it go on forever? We addressed that earlier. We're not sure. If it is finite, what lies beyond? Perhaps nothing we can comprehend. Or perhaps our three-dimensional space is embedded in a higher dimensional reality. String theory suggests extra spatial dimensions we don't perceive, perhaps curled up small. Could it be that our space is like the surface of a balloon, and there is a higher dimensional space outside it? If so, that's outside our experience, and possibly forever inaccessible. Or maybe beyond all galaxies, beyond the cosmic horizon, space just continues, with more galaxies ad infinitum. So even space, the very fabric we exist in, holds mysteries. Some researchers think space and time might be emergent from something more fundamental, like quantum entanglement patterns or spin networks in theories of quantum gravity. Imagine if space-time is not the base level of reality, but a kind of approximate large-scale picture that arises from microscopic physics that isn't in space-time at all. This is speculative, but we already have hints that space and time break down at extremely small scales. The Planck scale, around 10 or 35 meters. At that scale, quantum foam might be so wild that the notion of a smooth space-time becomes meaningless. Space might be chunky or erratic, full of baby black holes popping in and out, wormhole connections blinking open and shut, a true quantum chaos. We have no microscope to see that deep. It's far beyond our current or foreseeable technology to probe distances that small directly. But mathematical attempts at quantum gravity, like loop quantum gravity or aspects of string theory, suggest space-time could have an atomic or quantum structure. If so, then asking about the continuity of space or the absolute beginning of time might be like asking where exactly a flowing river ends when it fans into a delta. Up close, the distinctions blur. We cannot now answer if time had a beginning, or if space has an edge, or what space is made of, if anything. But we can marvel at the fact that we, ephemeral beings made of cosmic bits, can even frame such questions. Think of the journey, from silent stillness to swirling galaxies, to starshine on primordial Earth, to life evolving in the oceans, to human minds reaching out with curiosity. We are a way for the universe to know itself. That poetic insight appears literally true. Our senses, our instruments, extend the universe's ability to perceive. Without conscious observers, would the majesty of the cosmos have any meaning? The galaxies would still dance, the stars would still burn, but there would be no appreciation, no insight, no knowledge. Through us, and maybe through other conscious creatures out there, if they exist, the universe gains the gift of self-awareness. We are the cosmos made conscious, and so we are a small part of the cosmos, looking back at itself and trying to understand. It's as if the universe has sprinkled seeds of awareness within itself, and those seeds, in the form of beings like us, awaken and stare out in wonder, asking questions. We ask about the Big Bang and black holes and quantum foam, but in a sense, the universe is asking those questions through us. Space itself speaks in our questions. The great silence of outer space finds a voice when a scientist in a lab theorizes or an artist at night paints the Milky Way. We feel the mystery and we respond with curiosity, a fundamentally human trait, perhaps a fundamental cosmic trait expressed through humanity. Where do we go from here? The unknowns beckon us forward. We will keep building better eyes, telescopes to hunt for exoplanet atmospheres, to watch the birth of stars, to glimpse the first galaxies forming not long after the Big Bang. We will keep listening for signs of life or intelligence beyond Earth, refining our methods, maybe sending new messages or probes to nearby stars. We'll continue to smash particles together or devise clever detectors deep underground, hoping to catch whispers of dark matter or new physics. We'll push quantum theory to its limits, perhaps eventually developing quantum computers that might simulate aspects of reality we couldn't before, giving insight into those mysteries. Perhaps one day we'll integrate gravity and quantum mechanics into a single, coherent theory. A momentous achievement that could answer some of those questions, maybe revealing what really happens at a singularity or exactly how space-time emerges. And as we do, new questions will arise. Perhaps solving dark matter and dark energy will lead us to other puzzling phenomena. Perhaps understanding consciousness will open entire new realms of science about subjective experience. There's also a chance that some mysteries remain mysteries, either because they are fundamentally beyond our cognitive reach, or because obtaining the evidence is practically impossible, like a multiverse beyond contact, or what before the Big Bang was, if that concept even applies. But even then, exploring these ideas can enrich us. They make us grapple with the limits of knowledge, with the meaning of reality. Throughout all this, one truth remains. To not know is not a failing, but a feature of our existence. If we knew everything, the universe would lose its allure, its dynamism. Each of us in life starts not knowing, then learns, and in learning, discovers more things we don't know. A child might gaze at the sky and not even know what stars are. Later they learn, but then new layers of mystery unfold. What are stars made of? How did they form? The questions grow with the answers. This is the engine of discovery. Our ignorance is vast, but it is the dark canvas on which we paint our understanding. Imagine if every answer were handed to us complete. We'd have knowledge, but no journey, no adventure. It is the chase, the pursuit of truth, that often gives us purpose and joy. The moment of revelation, eureka, is sweet, but it is earned by the long not knowing that came before. And so, even as we strive for answers, we can find peace and wonder in the open questions. The cosmic mystery isn't something to be sad about. It's something to celebrate. It means we are intimately connected to a universe that is richer and more profound than our current imagination. It means there will always be new horizons to seek, new truths to uncover, or at least ponder. Picture yourself under the night sky again, as in the beginning. The stillness of the air, the silent twinkling of ancient starlight. You feel the immensity above and around you. In that moment, you are aware of a grand ignorance. You don't know what all is out there, or why it exists, or if someone might be looking back. Yet you are also aware of a profound connection. You are made of this universe's elements, your bones calcium from long-dead stars, your blood carrying iron forged in supernovae. The very act of you wondering ties you to the cosmos. Your questions are like a bridge between your mind and the infinite. Yes, the void is silent, but in our minds, that silence begets a quest. We fill the quiet with our inquiries and our explorations. We send out spacecraft, like extending our senses to the planets and beyond. We smash particles to glimpse creation's most microscopic secrets. We invent mathematics to describe black holes and quantum waves. We contemplate philosophical implications of time and existence. These are our conversations with the cosmos, and though it may not answer in words, it answers in wonders. We find one day a new kind of particle, or see a new kind of galaxy, or decode a new signal, and that is the universe's reply, telling us a little more of its story. Perhaps the universe also answers through our own self-discovery. The more we learn about nature out there, the more we reflect on ourselves. We realize how precious life is, seeing how hostile most of space can be. We see Earth from space, a pale blue dot, and it triggers a global awareness of unity and fragility. We understand that we are but one species among many, on one planet among many, in one galaxy among billions. This perspective can evoke humility and also a sense of fellowship with all existence. In cosmic timescales, human civilization is just a blink, and an individual life not even a flicker of a star. But to us, our lives are everything. They are our personal universe of experience. The big cosmic mysteries often reflect in microcosm in our personal mysteries. We wonder what our purpose is, how our minds work, how to find meaning in the vastness. And the answers are not handed to us. Each person, in a way, lives their own questions and gradually, hopefully, lives into answers. In that, we mirror the cosmos. Each of us begins in the darkness of not knowing, and along the way, we gather light. The process is continuous and perhaps infinite. In the end, after traversing all these wonders, from the birth of the universe to the nature of space, from dark matter to consciousness, we come back to a simple human truth. To not know is to be alive. Our ignorance is not just an absence. It is the driving force that keeps us searching, learning, striving. As long as there are things we don't know, we wake up in the morning with curiosity burning in our hearts. As long as mysteries abound, we have reason to marvel and reason to push boundaries. Imagine a final theory of everything that answers all possible scientific questions. Would curiosity die? Perhaps it would shift inward or to new realms, like creating art or simulated universes. But as long as we retain any sense of wonder, we find new questions. Even if somehow we understood the entire physical workings of the cosmos, we might still ask, why is there something rather than nothing? Or, what is the ultimate meaning of it all? Those questions might never have definitive answers. They're asymptotes we approach but never reach. And so we will always, in some sense, not know, and thus always be reaching, always growing. This endless pursuit is a beautiful thing. It means we are participants in a cosmic story of discovery, not just passive beings. The universe is not a static riddle to solve and be done with. It's a living conversation. Today's unknown will be tomorrow's known, and tomorrow's known will open up another unknown beyond. We stand on a threshold at all times. Behind us is knowledge hard won. Before us, the ocean of mystery. And isn't that what makes life and the cosmos endlessly fascinating? If the universe were small and simple enough for us to easily grasp in totality, it might lose some majesty. Its very unfathomability is part of its grandeur. The cathedral of stars overhead, the equations that describe them, and the equations yet to be written all form a grand, evolving tapestry. We humans are but a tiny thread in that tapestry, yet we can observe the whole pattern and add our own embroidery. Our scientific instruments are like extensions of our senses, giving the universe new ways to look at itself. Our poems, paintings, and music about the stars are the universe expressing beauty through us. We often personify the cosmos in our musings, calling her Mother Nature or envisioning gods in the sky, because deep down we feel that intimate connection, that we and it are one. And indeed, we are not separate from the universe. We are the universe, in the form of conscious living matter. Thus, the questions we ask the universe, we are in a way asking ourselves. And when we find an answer, we are the universe knowing itself a little better. Perhaps that is a kind of purpose we can latch onto, to be the mind of the universe, ever awakening further. If star systems are its body, perhaps civilizations are its mind, flickering on and off in the vast epochs, maybe one day linking up if interstellar travel or communication becomes possible, forming a network of cosmic awareness. Or maybe each remains an isolated island of thought. Either way, in us, the cosmic ocean has evolved eyes and brains that can map its shores and begin to chart its depths. The journey of not knowing to knowing and then finding even more not knowing is likely endless. And that is good. It means our descendants, be they human or augmented or AI or something beyond, will always have new frontiers. Just as we looked at moons and said, we'll go there, and did, they might look at other stars or dimensions or layers of reality and find ways to reach or comprehend them. Each answer, the moon is barren, Mars had water, black holes exist, spurs new questions. Could life endure on Europa? Could we terraform Mars? Can we travel through a wormhole? The quest fuels itself. Standing under the cosmic sky, we may feel small, but we are also giant in what we carry. the spark of curiosity, the flame of consciousness. The distances are huge, the mass is immense, the energy is unfathomable. Yet none of those physical things inherently produce meaning. A star doesn't seek meaning, a galaxy doesn't appreciate beauty, but we do. We create meaning by examining the cosmos and by simply living and loving within it. Our unknowing and desire to know give the universe meaning, as much as our capacity for joy and love do. In the stillness of a clear night, if you listen closely, you might imagine you hear the stars whisper. Of course, space is airless and there is no real sound, but there is a metaphorical voice, the voice of wonder that arises in your own mind as you behold the stars. That voice quietly says, "There is more, so much more." It invites you to ponder, to go further than those who came before, even if just in thought. It's the same voice that led ancient people to map constellations, that led Copernicus to propose the Earth moves around the sun, that led Einstein to envision riding on a beam of light. It's the cosmos, through the medium of human imagination, urging itself on to greater self-understanding. We do not know if we will ever find all the answers. Probably we won't, because each answer breeds new questions in an endless cycle, but that is the brilliance of it. We are alive in an epoch where mysteries abound, and likely every epoch will be such an epoch. We get to be explorers of the grandest kind. Whether we sail actual ships across space or ships of thought across higher dimensions, we are adventurers. Not knowing is the call to adventure. Curiosity is our compass. Each piece of knowledge hard won is a treasure we carry, but the treasure map always extends further. To be alive is to stand on that shoreline between known and unknown and feel the enticing breeze of mystery. It reminds us that we are part of something far larger than ourselves, and yet we belong. We belong in this universe as naturally as photons and quarks and nebulae. We fit because we evolved here and of it. The atoms in our bodies were forged in stars. When we die, those atoms will return to the Earth, perhaps one day to new living beings, or drift into space to join a new star. We are a transient pattern in a much larger flow, but while the pattern holds, we have the privilege of witnessing and wondering. In that sense, our not knowing is even comforting. It guarantees that the tapestry of existence is rich beyond measure. It means there will always be more to learn, more to experience. The cosmos will never run out of surprise and majesty. We humans sometimes fear the unknown, especially on the personal scale. The unknown future, the unknown outcomes of our choices. But we also thrive on the unknown, turning it into the known bit by bit. The key is to accept that uncertainty is fundamental to life and even to the universe. We will never have absolute certainty about everything, and that's okay. That leaves room for faith, for hope, for creativity. It leaves room for us to make choices. If everything were predetermined and fully known, existence would be like reading a book with no alternate endings, interesting perhaps, but static. With uncertainties, we write our own pages as we go. The great cosmic questions, then, are both scientific and existential. What is the universe? How does it work? Blends into, what does it mean for us? What should we do? There is no single correct answer to that latter part that science can give. But perhaps the very act of seeking answers is part of the meaning. Perhaps the growth of knowledge and consciousness is one of the universe's purposes, if such a word can be used. We often imbue purpose in things that might inherently have none, but maybe that's our role, to create purpose. If the universe was initially without meaning, we give it meaning by caring, by exploring, by marveling. And oh, how marvelous it is! This strange existence, where a primate brain can comprehend the birth of galaxies and the death of stars, where mathematics scribbled on paper can predict black holes, and then the sky shows they're real, where we can read the genetic code that links us to every creature on Earth, and yet still scratch our heads about what consciousness is, or how quantum entanglement actually operates. We solve pieces of the puzzle only to find new pieces beyond the edge. It's like an infinite game, and perhaps that is the secret. Life is an infinite game, where the goal is not to win. You can't, since there's no finish, but to keep playing, to keep the game going. In this game, every new insight is a level up, every new mystery a new quest. Eventually, billions of years from now, our sun will swell into a red giant and scorch the earth, a reminder that even the local theater of life has an expiration date. By then, if life from Earth is wise and ambitious, it would have spread out to other stars, preserving and expanding the chain of knowledge and being. The universe will continue to evolve. Galaxies will drift apart. Stars will exhaust their fuel. Trillions of years hence, starlight might wink out as the cosmos grows cold and dark, assuming dark energy doesn't do something even stranger like ripping space-time itself. But that is an unimaginably distant future. In the meantime, we have an abundance of time and possibilities to savor. And even in that far, cold future, perhaps the descendants of our descendants, or whatever life becomes, will have unlocked deeper truths, maybe manipulating dark matter or energy, maybe tapping zero-point vacuum energy, maybe even creating baby universes to escape into when this one grows old. We can dream far indeed. Whether those dreams come true or not, they highlight our refusal to accept limits without probing them. We always seek a way, an answer, an extension. If the universe is expanding, we figure out how to navigate it. If life is rare, we treasure it and propagate it. If knowledge is hard, we train more minds and build better tools. In the reflective silence at the end of our journey, we return to ourselves, here and now. We think of all we have pondered, a universe with billions of galaxies, mostly unknown, mysterious dark matter and dark energy, sculpting fate, black holes challenging our physics, time flowing irreversibly from an ordered dawn, quantum particles dancing an unpredictable dance, countless stars with unknown planets and maybe unknown life, our own fragile existence with a mind that defies full understanding. It's a lot to hold in one head. So we breathe and we realize it's okay not to have all the answers. It's okay, even beautiful, that there is so much we don't know. It gives us room to be curious, to be astonished, to be human. The night sky remains as it was for our ancestors, profoundly mysterious, compellingly beautiful. We have explanations for the points of light now, suns, not God's campfires or what have you. But the experience of awe is undiminished. If anything, knowing how vast and how ancient those stars are makes the night more awe-inspiring. The knowledge and the mystery together weave the full tapestry of wonder. Science and poetry meet when we confront the sublime. In that spirit, we end not with a conclusion, but with an embrace of the open questions. The universe's narrative is still being written, and we are part of the writing. Our knowledge will continue to grow, but never exhaust the mystery, and thank goodness for that. The cosmic silence is not emptiness. It is a canvas for our curiosity and imagination. The stillness is not lifeless. It is pregnant with all that we have yet to discover. And the birth of a question is perhaps the greatest gift that the darkness gives to the light of mind. We remain, as ever, small creatures with big minds, suspended between the infinitesimal and the infinite. We seek, we find, we question again. The cosmos doesn't hand us a manifesto of meaning or a clear roadmap. It simply is. But through our not knowing and our relentless pursuit to know, we craft a meaning. In the quiet dialogue between our minds and the stars, we find meaning in the very act of seeking. And so, let us cherish the mysteries. Let us cradle our ignorance softly, not as something shameful, but as the wellspring of all fascination. When we feel that itch of the unknown, when a child asks, "Why?" How? What's beyond? Or when we ourselves stare at some deep paradox of physics and feel perplexed, let's smile. That is life. That is the universe, nudging us onward. Each "I don't know" is an invitation. As long as we accept these invitations, we are truly alive, truly participating in the cosmic story. In the vast darkness, a question was born, and from that question flowed all our science, art, and dreams. We do not know all the answers, and likely never will, but we continue, eyes open in the dark, hearts receptive to wonder. For it is in not knowing that we remain curious, and it is in being curious that we remain alive in the fullest sense. The universe, speaking through silence, asks us questions in the language of awe and mystery. Our lives are our answer, an answer expressed in exploration, in love for truth, in reverence for the unknown. In this way, to not know is not just to be alive, it is to be authentically, exuberantly alive, a participant in the grand adventure as old as time and as wide as space. So let the mysteries be, and let us embrace them. Under the silent stars, feel your heart beat with both wonder and peace. The cosmos is vast and strange, and we are an inseparable part of it. In our very inability to grasp it whole, we find our place within it, searching, discovering, and marveling. This is our endless story, the slow, poetic, immersive journey through a universe of questions. And as long as questions remain, life remains vibrant. To question is to live, and to live is to bask in the unknown, even as we reach for understanding. Indeed, to not know is to be alive.